Okay, thanks. Great recording. Okay, I thought we all had permission to record. Apparently not. Okay, so yeah, so this is one of 3 courses that are going to start this week, and then the PhysiCell and the CompuCell 3D will follow. Both those 2 subsequent courses are from Bloomington, Indiana, James Glazer's group and Paul Macklin. Both of those courses go beyond this. We will deal just with subcellular modeling and our particular tool, Tellurium and Roadrunner. They will focus on multi-cell modeling. They have their own tools, but actually underneath for all the subcellular modeling, they do use our tools. So you'll be able to reuse what you learned this week, next week. So this is going to go from Monday to Thursday. It's about 6 hours a day plus break, 7 hours a day plus a lunch break. Plus other breaks in between, so it's less than 6 hours, probably, well, I'm not sure, 5 hours total a day. It goes from 8 o'clock in Pacific time to 3 o'clock in Pacific time. So hopefully some of you are not coming in on very awkward times, but maybe you are. What else? Yeah, so the lectures are hopefully short. This morning might be a bit different, but most of the lectures are going to be short and followed by exercises. We don't want you falling asleep halfway through a lecture. So we try to keep them short, and then exercises, lectures, exercises, and so on with breaks. We did this last year. It seemed to work okay. All right, so who's involved in this? So we have a number of instructors who are going to be helping out today. You may have heard Lucian Smith just speak up there. He's in the bottom row. Lucian. Veronica is the main contact person. She's basically organizing she's in the top left corner. She's organizing the summer school. And then the other instructors are Joe Hellerstein, who's a data scientist here at the University of Washington. And oh, yeah, and Lucian is also going to present as well, and Veronica is going to present as well. So there's 4 of us presenting. There are the other people, Lillian, Janice, Michael, and Jin will be manning the Slack channel, and so will Lucian and Veronica. If you have any questions, send them into the Slack channel. If you don't have the Slack channel, just send them into chat, okay? All right, so, all right. I guess I could ask first if there are any questions from anybody. If you have any questions now, you can put them into the chat. Otherwise, we can continue. All right. And don't be afraid to speak up if you have questions or clarification points to make. Okay, so the first thing is we have a Google Drive. This is the URL. We have a Google Drive. I'm going to put this into the chat window if you don't have it already. So we put this into the chat window. This is where everything, all the material is kept. And hopefully this link will also be posted to the Slack channel as well. Now in this Google Drive, we have a whole lot of stuff. We have the daily schedule, the cheat sheets for the modeling and Tellurium. There should be a document on Nutshell. I need to check that actually later. There's a folder for each day, so day 1, 2, 3, and 4. In each folder, you'll find a morning and afternoon. Well, actually, it's not morning and afternoon anymore because of the time zones. It's actually session 1, session 2. And in those, you'll find scripts, PowerPoints, exercises, and so on. And all the recordings. I think we decided the recordings will go onto YouTube because they take up so much space on Google Drive. We have limited space on the Google Drive, so I think they'll be uploaded to YouTube. So this
probably put a link on the. You can probably put a link in the drive to the YouTube thing once it's there.
Yeah, once it's there. Yeah, good idea. Yeah. The other thing is the piece of software we'll use is called Tellurium, from the element Tellurium. It's a Python-based package. The documentation, I'll put this into chat as well. Oops, hold on, excuse me. Let me put this link into chat as well. So you'll see that. So that we have a lot of documentation on this software. This is a cross-platform piece of software, works on Linux, Windows, and Mac, and clusters, supercomputers, and so on. It's Python-based, but it talks to a very high-performance simulator underneath called Roadrunner. And this is the software that we'll be using this week to do our exercises and so on. Roadrunner itself is used in quite a few places as a back-end simulation engine. A lot of multi-cell modeling platforms use it, and a number of other simulators use it. So once you've learned this, once you've learned the syntax for this, you'll find you'll be able to reuse it in other platforms too. So some of the basic topics we'll be doing, I think the Thursday thing has slightly changed, but is basically what we were doing, ranging from how to build basic simulation models, how to do some model fitting, and then other topics such as reproducibility and verification validation, and a piece on model repositories and how to distribute your models will be given as well. Okay, so in computational science, we have two broad groups of software that people use. We have the graphical user interfaces. Probably the most well-known in the systems biology domain is Copasi. Nice thing about graphical user interfaces, as we all know, they should be easy to get started, though there's no guarantee of that. You can easily make a graphical user interface that's almost impossible to figure out how to work. But in general, their advantage is that they're easy to get started with, and you can get something running pretty quickly. The limitation, of course, is that you're limited by what the author has given to you in terms of the GUI interface. Okay, so there's a limit to what you can do. The other approach is to use scripting languages, and these are really popular. I mean, the big ones, of course, are MATLAB, Mathematica, things like that. There are a lot of open source scripting languages like Python, of course, and Julia and R and so on. These tend to be a bit harder to get started. Again, not always the case, but you have to learn the language in order to get to use them. Python is a good choice because it's relatively easy to use. The nice thing about scripting languages is that you have unlimited possibilities. Nothing is really baked into stone. You're just limited by your own imagination as to what you can do. But with that comes the fact that it's a little bit harder to get started. So I'm a big fan of scripting languages. If you're a power user, that's basically what you'll be using to build models or any kind of computational science. But graphical user interfaces are very handy if you want to get something done quickly. There are also a couple of online simulators like JWS Online, Easy Model, VCell, and so on. They're also GUI based, and they're also easy to get started with too. But again, they all have limited functionality, because they're a graphical user interface. So in scripting languages, then I guess here are 5 big ones I put out. There are probably others that you could mention. The 2 big commercial ones are MATLAB and Mathematica. The 3 big open source ones, at least for computational science, are R, Python, and Julia. Now, both MATLAB and Mathematica are extremely good platforms. I mean, they're backed by a corporation, so they have good resources. The open source ones tend to be developed by volunteers and so on. So they're not as perhaps things like Python, R, and Julia are not as polished perhaps as MATLAB and Mathematica. Now, the only downside with using something like MATLAB and Mathematica is that the algorithms they use are largely closed. This is especially the case for Mathematica. I remember one calculation with Mathematica to compute the null space or kernel of a matrix. It did a really nice job of calculating them, but nobody had any idea how they did it. And then a couple of versions later, they changed the way they must have done it. And the original one were in the form of what's called a basis. The subsequent ones weren't, and so there was a change. And because we had no idea what was going on underneath. So this is one of the issues with using proprietary software, especially for open science, you don't actually know what the algorithms are used. MATLAB is better at this than Mathematica, but Mathematica is particularly difficult to know what it actually is doing under the hood. Of course, the other issue, of course, these are expensive platforms. Mathematica is, well, $1,000. MATLAB similar. So that limits their broad adoption across the community. So if you develop something in MATLAB, you can't guarantee that, you know, the person you send it to has a copy of MATLAB either. So, okay, so we picked Python, and probably some of you already know Python, and you know what the advantages are. You know why Python. Python's been around for, I'm not sure how long now, over 20 years, I think at least. It was developed originally as an educational effort, but has now morphed into something that's used day in, day out, pretty much across all disciplines. The fact that it was used originally as an educational effort meant that it had to be easy to use, and of course that's why now it's also popular. So it's pretty easy to learn, pretty easy to use. You can pick things up pretty quickly. You can get a lot of work done in Python just by knowing only a little bit of Python. You don't have to know the depths of Python to make it useful. Of course, some high schools are now teaching it, so it's widely employed from high schools to industry. There's a huge amount of online support. And those of you who follow the, you know, the top 20 programming languages, you know, of 2021 or 2020 will know that Python is one of the top 3. So, and because it's one of the top 3, there's a huge amount of online support. I don't know how many courses there are on Python. There must be thousands across the globe. And it's also, for various reasons, surprisingly used a lot in computational science. Because a lot of AI is done now in Python. So there's quite a few packages in systems biology that employ Python, and it's becoming even more. I mean, it's already very popular, but it's becoming even more popular. Now, the disadvantages of this, it can be slow, which is why a lot of people just use Python as a glue. So you don't actually do the computationals necessarily in Python, but you use Python to access some high-performance computing engine underneath, which is usually written in C or C++. If you try to do your computations in Python itself, it can be quite slow. I mean, significantly slower, maybe up to 10 times slower. It is getting faster though. Since version 3.4, we're on version 3.9. It's actually got faster quite a bit. And there's a new effort out that's about to start to try to double the speed of Python in the next few years. But as I say, that's not really a big issue for us, because if you do have something that really takes a lot of time to compute, you won't do it in Python anyway. You'll just call it from Python, which is exactly what we do. So Roadrunner, which is the simulation engine, is written in C++. It actually generates machine code in the back end, so it's very fast. We just call that from Python, and we've made it very easy to do that. So where do you get it? I should point out this course is going to be from the very beginning. It's going to start from, you know, assuming you don't know very much at all. So some of you may know some of this already. I mean, we're going to do an intro to Python this morning. Some of you may already know Python, so you can drop out if you want this morning or this first part of the morning and do something else. But this course is going to begin assuming people know hardly anything. So, for example, where do you get Python from? Well, the primary site is, surprise, surprise, python.org. So if you go there, you can get hold of it. Now, the only trouble there is what you get is a fairly bare bones Python. It's a very primitive interface. It's not one you use for real work. And so instead, what people have done is they've built these fancy user interfaces that use the bare bones Python, right? So people soon realized that the raw Python you download from python.org is a bit too primitive for daily use. I mean, you can use it, you know, you can use it for doing work, but it's nicer if you have something a bit more elaborate. And so people created more fancy interfaces that Python, not people, could be used from. So it still uses the Python from python.org, but it adds this extra face onto it. And 3 common ones here are Spider, PyCharm, and Visual Studio Code. All these three work across all platforms. They're all available for free. Different people use different ones for different reasons. And this is for desktop use. Right? So if you're on the desktop, you either get hold of Spider, PyCharm, or Visual Studio Code. They all have different advantages and disadvantages. And we'll talk about these later in the week. There is another approach to using Python and other scripting languages like R, which has become more popular in recent years, and that is the notebook. So the most well-known of these is the Jupyter Notebook. Some of you may have come across this already, and that's what we will be using today, is a Jupyter Notebook. Jupyter Notebooks they are web applications. They can either be used remotely in a browser, right, to a server, which is what we'll be using, or you can actually use a web-based application on your desktop also, and you can run what's called a Jupyter Notebook. So it can be run from the web or the desktop. Basically, this is what Visual Studio Code is. Today we'll be running everything from the web, from something called Colab or Colaboratory. So Colab is a service provided by Google. It's another free service. You wonder how they make money at all. It's really nice thing to have. It basically means you don't have to install anything, which is what we wanted to get away with this week. Often, it can take a while for people to install their software on their machines, and sometimes there's the odd issue. To avoid all that, we decided to go with Colab, where you just log in and you're ready to go. Towards the end of the week, we'll talk about, you want to use the software on your desktop, then we will talk about that. So what is a Jupyter Notebook? Well, it's an interesting idea. It's those of you who use Mathematica, it's similar to that, where you basically mix code with documents. So it's sort of it becomes a live document. So if you were to write an article, for example, in Jupyter Notebook, you'd have a whole bunch of text and sections and so on. But interspersed, you'd have actual live code, which you could run, and that code could produce plots and so on. So it's a fairly dynamic document. What's really good about it is if you have done a study, you can then package it up as a Jupyter Notebook and pass it on to someone else. And then it's much easier for them to use it, because it's fully annotated with text and so on. It's not so difficult to understand instead of just raw code. Okay, so we're going to start now in a second. Are there any on some actual work? Anybody got any questions or queries? If you have, just pass them into the Slack channel or the chat. Okay, we got nothing yet. Okay. So the first thing I want you to do.
Actually, there was a question in the Slack.
Yeah.
What was the other? You mentioned JWS Online as an online simulator. What was the other one you mentioned?
Easy Model.
Easy Model.
Yes. So there's something called Easy Model. So if you just type Easy Model, it should get you. Actually, it doesn't. But if I type Easy Model, maybe simulation. There you go. Well, that's the paper. Easy Model. Let me see. Let me see if I can find it. That's the paper. Oh, there it is. There we go. It's a funny URL. It's edl.cat. Anyway, so this is another thing that you can try and use. There we are. Welcome to Easy Model. I have nothing to do with these people, so I'm not trying to advertise anything. But it can be something that you can try out as well. I believe Kopazi has an online thing called Shiny Kopazi, I believe. Is it Shiny Kopazi, something like that? Here we go. Yeah, Shiny Kopazi, which basically they just take the UI, the raw UI they have, and then slap it onto a browser. So that's a quick way of getting hold of Kopazi if you don't want to download it. And of course, there's JWS Online. Okay, all right. So let's close those. Okay, so first thing you want to do is to get yourself to Colab. Okay, so let me see. Way to get to Colab is to actually just type Colab at the search, Google search. If you type Colab, first thing you should get, of course, it depends on what part of the world you're in, but first thing I get anyway is the Colaboratory link. Okay, and if you click that, you get to the, what you'll actually get is this page. All right, so you'll get something that looks like that. So that's the first thing we want you to get to is Colab. All right. Okay, yeah, so this is what you should see. So if you type Colab in the Google search bar, first search entry, at least for me, is the one I want. And this is the page you should see. Okay, if anybody is having trouble, just post a message to Slack. Okay, so let me expand this again. Okay, now let's see if we can get it working, shall we? So first thing you want to do is in this page, you want to go to the file menu. Okay, so let me do that. I'm going to go to the file menu. So I'm on this page here, and I'm going to go to the file menu. Okay, and then I'm going to go new notebook. If you go to new notebook, it brings up a new page. All right, and it has a title. In this case, it's untitled. You can call it something if you like. You can call it hello. Okay. All right. Now it has an unusual file extension. You can see the pi in there. That refers to Python. The NB refers to the notebook. So this is a Python notebook we're building. So once you've got to this point, you'll notice that you have a menu bar. You have something called plus code and plus text, and then you have a side toolbar as well. But then you have this very important thing here, this strip with this black arrow button on the left. Okay, now if you click on that, you see the cursor starts blinking. All right. To check that it's all working, let's type the following: print, and then brackets, and then in quotation marks, type whatever you want. Welcome to 2021 summer course. Okay, so you can type whatever you want there, but type something. So this is just to check that you've got Colaboratory working. So now how do I get that to run? Well, that's what this black arrow is for. There are actually two ways to get this to run. The obvious one here is this arrow button. You can just click that. The other one, which is not so obvious, but it's something. If you're a keyboard person, it's the one you want to use. It's Shift Enter. Okay, so if you hold down Shift and press Enter, it'll execute this thing which we call a cell. I'm just going to do it by clicking on the black button there. It may take a few seconds to start up as it spins up a virtual machine for you. Once it's done that, it prints out the message, welcome to 2021 summer course. Okay. So has anybody got any problems getting to that point? Okay. All right. All right, next thing. So we've got to this point now where you've got notebook running and you've managed to print out a hello world or some other message. Let's go on to the next slide. There, that's what you should see if that was successful. All right. Okay, so before we just launch then into the introductory to Python, I just want to say a few things about versions, which may, if you're new to Python, this may worry you. The good news is there's nothing to worry about. Python has been developed over many years, and they produce new releases every now and then, called versions, and these versions have numbers. The current version that's active is 3.9. We happen to use 3.8 in all our desktop work, but Colab uses 3.7. So you can see that we all use different ones. The good news is it doesn't matter at all which of these you use. Okay. So if you're on the desktop and you happen to use 3.8, then you move your code onto Colab with 3.7. Don't worry, you won't have any problems. All right. Even if you go to 3.9, there's no problems at all. So don't worry about the versions. What I don't recommend is going below 3.7. So don't go to 3.6 or 3.5. And those of you who know a bit about Python will know there's a 2 series, 2.7 being the latest one. That is being discontinued in terms of support by Python organization. We do not use it anymore. We do not support 2.7. Okay, so stick with one of these 3 top ones, 3.7, 3.8, or 3.9. Okay. So what we're going to do is we're going to get hold of a Python notebook. And the question is for you is, where is it? This is the first thing that we'll see how good we get on with. So this is the basic structure of our Google Drive. We have the lecture materials, and then we have the days, day 1, day 2, day 3, day 4. And within the days, we have sessions, session 1 and session 2. So we're currently obviously on day 1, and we're in session 1. You want to go into session 1, all right? Let me just show you where it is. So this is my Google Drive here. So actually, this is the old one. Let's go back here. So if I go back to 1, so that's lecture materials, which you probably should have access to. Go to day 1, go to session 1, and you'll see this material for this morning, all right? Okay. There's 3 things here. There's the PowerPoint slide, which we're currently looking at. There's the introduction to Python notebook, and there's another series of slides there, and then there's a data file. Okay, so there's 4 things you should see in that folder. Okay. So if I go back to my slides, so this structure then reflects what you just saw. So what we're going to do is we're going to learn some basic Python. Some of you may already know this, in which case you can, do something else. Well, this might take half an hour, 45 minutes. I don't know how long. We're going to learn some basic Python from the ground, from the beginning, as if you don't know anything. So we need to get hold of the intro Python notebook. Okay. Oops, sorry. You need to get hold of the intro Python notebook, and that intro Python notebook is this one. Okay. All right. Question is, how do you get hold of it? There's a couple of ways to get hold of it. You notice that my little intro Python has this funny little orange squiggle, this sort of infinity symbol, is it, or something like that? That actually tells me that Colab recognizes this as a Python notebook. And in fact, if I right-click over this, right-click, I'm not sure what you do on the Mac, but on Windows and on Linux, I think you just right-click. You'll see you have open with. Now, some of you may have an entry here called Google Colaboratory. If you don't, you could try connect to more apps, and then you could just search for Colab. There it is, and you'll find it. Then I've already installed it. Okay, so it says it's already installed. But if you haven't got it installed, you'll be able to install that, now at this very moment. You can see it's got over 5 million installs, so it's pretty popular. So if you install that, so let me show you how to do that again. If you don't have this, so right-click, open with. I happen to have Google Colab here because I installed the plugin. If you don't see that, you'll instead see Connect More Apps. You click on that. That'll take you to the plugins, Google Workspace Marketplace. And then in the search, just type Colab. It'll come up with Colaboratory. And then just click on that to install, right? It'll only take you a few seconds. And once you've done that, then you'll be able to right-click and Google Laboratory. Now, what happens if, for some reason, you can't do that? All right. There's a straightforward way to get around this. If you right-click on it, download the file to your computer. Okay, so download the file to your computer. So let me do that now myself. Download, and then put it somewhere convenient. I've already downloaded it there. It's intro Python IPYNB. Okay, let's pretend I've downloaded. I won't say save here now. I'll just put cancel. But you would save it to your download folder or wherever is convenient. Okay. Then what you will do is, so by the way, what happens? Then what you'll do is you'll then go to File, So you go back to Colaboratory, you go to File, and then you go Open Notebook. So not New Notebook, but Open Notebook. And it gives you all this stuff. This is a biggish screen here with examples, recent Google Drive, GitHub, Upload. If you go to Upload, you can choose the file from your local drive, okay? All right, so so I won't pick this one because it looks like it's an old one. So let me, I won't pick that one. I'll do it the other way. But for those of you who can't use the right click on the Colaboratory on Google Drive, you can just go Upload, choose File, and then you're ready to go. Let's instead do it this way. Right click, open with Colaboratory, and it'll open up a new browser window, and it'll load in the intro Python notebook. Okay, so hopefully we've all got to this point. All right, I'll wait a minute or two to make sure we all get to this point. Okay. If you have any questions, just send them to Slack or the chat. I know this is probably, some of you will probably, this is very, very straightforward to you, but because we have a large number of people, we have to make sure everybody is in sync, okay? So just bear with us, for those of you who are raring to go, okay? All right, looks like there's no comments on chat or Slack, so I think we'll carry on. Okay, so let's talk about what we see in front of us here. So this is a notebook, this extension IPYNB, Jupyter Notebook to be precise. In this case, we're running Python. Jupyter Notebook can run other things like R as well, but you have to go to a different website for that. What we have in a notebook is a series of what are called cells. So here's one cell up here with print in it. Here's another cell with something that says it's a comment. Here's another cell with a comment, another cell with a comment, and here's a cell with 3 comments. So a cell can be as big as you like. You can have as much code in the cell as you want. Cells are useful for separating off, parts of your study. This is what I'm going to be doing here. So let's start off with this. Oops, I didn't want to do that. Never mind. All right, so I created a cell accidentally. Let me just delete that. So delete cell. So if you right click on a cell, you get these, extra things like delete cell, copy cell, and so on. So I just accidentally produced a cell. To produce a new cell, you can just go to either this plus code button and it gets a new cell. All right, now we delete that. Delete. Or if you hover over the just above the cell, you get the same one's code again. I can click that and I'll get a new cell as well. Okay, so let me just delete that. Okay, so I prepared this beforehand. There's a whole bunch of cells. Each cell, of course, can be executed. Each one has one of these little execute buttons. So I can execute my print hello world and it executes it. First thing to learn, well, the first thing you learned, of course, is how to print stuff out in Python. So that looks pretty simple. Print brackets, then put your message in quotations, okay? The next thing we'll learn is comments. These are parts of your code that will not be executed. And a comment in Python starts off with a hash symbol. Now, if I wanted to add more to this cell, I can just hit enter and it just gives me a new line in that cell. Then I can, print some more stuff, okay? All right, and to execute that, I can go to the black arrow here, click it, and it'll execute it, and I get the message, print more stuff, okay? All right, so the rest of the cells just summarize what I just said. Notebooks are made of cells. This is a cell, okay, this is a cell. By the way, these things over here, you can move cells up and down, okay? I can move the cell all the way to the top, all right, or move it back down, all right? So that can be useful for reordering things. This, let me see, we have reordered things now. So I'm out of, here we go, let's move that back up. Here we are, we're back in order again, I think. So this one here tells me in a comment as well that cells are executed using Shift-Enter or the black arrow button to the left, okay? So a lot of people, once you get used to this, will tend to use the Shift-Enter button on your keyboard. If you're a keyboard person and you don't want to move your hand to the mouse, this can be very handy. So if you basically put the cursor on the cell, and then you hold down Shift and then press the Enter button, and it executes it. Okay, that's what I just did. Shift Enter. All right. So it's not Enter. If you type Enter on its own, it just creates a new line for you to type new stuff in. Shift Enter executes. Okay. All right. Now, this is something I tell, my students all the time, especially after this course finishes, you might get stuck on something. I tell my students all the time, I mean, they're the internet generation, but they seem to forget this tip, which is that Google is your friend. If you're stuck on everything, you can do a quick search on Google. There's a site called Stack Overflow, which has a ton of stuff in it related to Python. I don't know if I haven't tried this, but we could try this, how to print text Python. I mean, that's a bit of a silly question to ask, but let me see if it gets me to Stack Overflow or not. Well, I could ask it to search Stack Overflow. There we go. So this is the Stack Overflow I'm referring to. Some of you know, I'm sure, know this already. But what Stack Overflow is, it's basically a series of questions people pose, and then other people come in to answer them. All right. So this one here was asked 8 years ago, 8 years and 6 months ago, printing a variable and a string in Python. And this person is asking a question, and then there's a bunch of answers, 7 answers down here. And you'll see that there's a little number next to the answer. These are votes by people who think the answer was really good or not so good. So the best answer is this one with 61 yeses. So anybody can ask questions on this. Anybody can answer questions on this. It's a very, very useful site. And there are Stack Overflow topics and all sorts of things, even cooking, I believe. So if you have a cooking question, you can also go to Stack Overflow. All right, where were we? Okay. Yeah, so Google and Stack Overflow and anything else you find on the internet, of course. All right. So now I'm going to show you something else about notebooks, and that's this thing here. You see, this is a title. It's not a piece of code. I can't execute this. So this is an example of text in a notebook, right? So a notebook can be made up of text, figures, and code, live code. And this is a title I made. If I double click on it, you see what it looks like inside. It's a little bit more involved than it needs to be. Actually, I don't need that. I wanted to change the color, and you need to use HTML to change color, so that's all I did here. But the title is basic data types. There's a whole bunch of little buttons up here that you can use to. In fact, let's do something, shall we? Let's create a list. Here is a list item 1. Okay. Oops, that didn't quite work. Sorry. Excuse me. Let me delete that. So here's some lists. So list item 1. So now I've got a list in my text, and you can put in paragraphs and all sorts of things. So it's very useful for the notebooks are excellent vehicles for sending your model or your computational experiment or whatever it is to someone else, because all they have to do is upload it to something like Colab. They don't even have to have the software on their machine, and they can immediately look at it. They can read your stuff and they go through it. It's great for doing courses and sharing computational experiments. Okay. All right. So this section is titled Basic Data Types. And by data types, I mean what kinds of data can we work with in Python? Well, usual obvious ones like floats. In fact, let me put a new one in here. Integers. There we go. That's an integer. I can put a comment in. This is an integer. All right. So I'm assigning an integer to a variable called I. Right. And let me add something down here. I'm going to print I. Oops. I, okay. I've got 2 doubles here, floating point numbers, and I'm adding them together to form a new variable, and I'm printing them out. So let's print these 2 out. just re-execute this cell, and I should get any second now 7.8 and 5, right? Remember, this is all the calculations here are going across the internet to one of Google's servers, which does the calculation and then comes back again. This is not being done on my local machine, all right? Which is why you get these sort of delays, all right? So if you've got a flaky internet, this may not be maybe something you want to use, but it works pretty well though. We have the normal arithmetic operators: addition, subtraction, division, multiplication. The one that can get people is the power operator. So it's, you'd think it, you would have thought, right? It might have been, oops, sorry. I jumped ahead there somehow. Where are we? Oops, sorry, here we go. So you might have thought that the power operator would have been the hat. So for example, I might have put something like, 2 to the power of 3. No, you don't do that. This is basically showing Python's age a bit because star was used in Fortran, and maybe that's where it's come from, I don't know. But star is the power operator. So if I run this one, 2 to the power of 3 is 8. Print X, I get 8, okay? So that's the only thing you have to watch there. Printing, the print statement is pretty flexible. I can print one thing, or I can print lots of things separated by commas. For example, some text. I can print some text as well. I can do a calculation in the print as well. So let's do 3 to the power of 4, not 23, 3. And then I can execute that cell, and I get that. So your print statement can be lots of things separated by commas. Variable names can be whatever you want. They can contain numbers and underscores. Obviously, you can't start a variable name with some kind of punctuation mark like that, punctuation letter like that. Always start them with a letter or an underscore. But you can have whatever kind of name you want there. And so we have here the essential variables are integers, floats, strings, booleans, true or false, and a very, very useful kind of data are lists. So a list basically is a collection of pieces of data. The data can be any type. They can be mixed. The other thing about a list is a list can contain a list itself. So here I have a nested list. So this list contains an integer, a float, a string, a Boolean, and then another list. And inside that list, I have a Boolean and a string. Now I could go crazy and put yet another list in here. Another list. Here we go. And I got a list inside a list inside a list. You can imagine you can go on forever. Let me execute this cell. And then execute this cell. And you can see now I've got another list in there, okay? So lists are really handy. I mean, we're working quite a bit with lists. Just a little brief thing about the arithmetic operators. They work as you'd expect. Just one thing about the addition, though, and this also applies to multiplication, is that you can add strings. Okay, so I can add a string together that basically joins the strings up. Right. I can also do the same with lists. I can add lists together. They basically just combine together. If I run this cell, and you can see I've run all these cells before. Let me just run it again. So X string now contains the full string, and X list contains the full list. Okay. What about more complicated math, logs and trig functions and things like that? Well, this allows me to introduce the idea of libraries. Python, one of the nice things about Python is it's really easy to extend Python in the form of libraries, and there are literally hundreds and hundreds of libraries available, probably thousands, maybe tens of thousands of libraries available for Python. There are some that are built in, that you get for free. There are others you have to install yourself, but that's there's a typo there. You can install yourself and make them available to you, and that's one thing we will be doing. So, but for one of the built-in libraries is math. All right, so to get hold of this library, I have to type the word import and then the name of the library, which is import math. Make sure I run it, and once that's loaded, I now have access to all the math functions. For example, cosine. So in order to get hold of cosine, I have to use the name of the math library, a dot, period, and then the name of the function I want, and then whatever the arguments is. So if I run this, I obviously get, -1. These are radians, by the way, so that's 3.1415, which is pi, of course. I get -1. You might be wondering, yeah, but hold on, what's in math? How do I know what kinds of things are available to me? There's lots of help available. Pretty much all the Python interfaces offer this feature where if you put a question mark after the function, I get help on it. So if you know what your thing is already, right, you can get help on it just by putting a question mark, and the little help string will come up here on the right panel. What happens if I have no idea what's in math? Well, one way to do it is to use the command dir, directory. Notice that the minute I typed dir, it came up with a help panel, right? That can be really useful. It says this thing returns a list of strings. If I type math into it, it'll actually return to me a list of things in math. And if I scroll down, you'll see there's lots of things. Let's see, there's the cosine, there's E, the Napier number. There should be pi here somewhere. Oh, there's pi. There's sine, square root, tan, log, all sorts of things. Okay, so just to show you, now that that's one way to find out what's in it. So I can go pi math.pi, and it confirms pi exists. So you can see that, and I get what happened there. There it is, pi 3.14159265, etc. Okay, so you can do this with all libraries. Some libraries also offer. They do a more fancy help where you can put the cursor in front of it, and I don't think it'll work on, well, we don't know, let's try it. Control I, and that sometimes brings up a much fancier help panel, which is all nicely formatted and everything. But if in doubt, just put a question mark and then run that cell. And as you can see up here, it says, oh, look, it's a floating point number. The string form is that. Funnily enough, it doesn't tell us what it actually is. It's pi, but never mind. Now we'll be importing libraries a lot, okay? So you need to get used to this idea of importing math. There are some extras that come with import. If your library name is really long, you can ask it to shorten it by going, let's say math is not that long, but let's say I wanted to shorten it to M. I would then go as M. And now I can just go m.cos, and it gives me the cosine, right? So if you want to, there are a couple of libraries like this where the authors have made really long names, and it's a bit of a nuisance to type the long name in all the time. You can shorten it with this little bit of extra syntax, okay? So in this case, import math as M. All right. Okay. We've got a couple of things on Slack. That's good. Yeah, people are asking questions and answering questions. That's great. Yeah, if you have any questions or things I gloss over or you want more clarification, just send them into the Slack. And anybody in the audience who'd like to contribute with answers, absolutely, please do so. Okay, so what we've shown at the moment is some basic variable types, some basic arithmetic, some tricks with strings and lists, importing libraries. So the next thing is going to be loops. Now, we're not going to teach you, the whole of Python. Python is a big library these days. But the nice thing about Python is you don't have to do much. You don't have to know much to really get a lot out of it. And so we're going to teach you some of the basics. And with those basics, you'll be able to do a lot with it. Okay. And then over time, then you can add to your knowledge by learning other tricks and pieces of Python. So I guess there's two things that because we need to know in any programming language is loops and if statements. All right. So every language has the ability to repeat things. Every language has the ability to test things, and depending on the test, do a certain operation. So let's open this open this loop cell. So here's a simple loop. Okay. So it's a bit of a strange looking loop, really. If you're used to something like C or BASIC, this doesn't quite look like loops you find in those languages. The 4 at the beginning is familiar, but the rest of it might be a bit strange. But what we have here are 3 things. We have a variable, which is the loop variable. This is the variable that's going to have the value of the loop as it iterates. We have this keyword in, and then we have a list. Okay, so we've already seen lists come in here, and this list contains all the numbers you want the loop to go through. So in this case, we're going to go through numbers 1 to 4. So this means it's going to loop 4 times, and each time it loops, it's going to pick out a number from this list and assign it to I. So if I were, so the only thing I'm doing here is starting a loop, and then inside the loop printing I. All right, then if I do this, I get 1, 2, 3, 4. There are 2 things you need to be aware of this loop, and this will apply to a lot of things we deal with later on. Things like loops, if statements, user functions, they all start with the first line like this, then end with a colon, right? If you don't have a colon, it'll get upset, right? And there it is, syntax error. I am upset, all right? So they all end up with a colon, right? That's the first thing. Now, the other odd thing which can take people, you either hate it or you love it. I eventually got used to it. Now I'm quite happy with it. It's this idea of indentation in Python. So in a lot of languages, you need to group things together, particularly in something like a loop, where you want to say, well, I want to do all these things inside this loop. And you want to be able to group these things. There are various ways to do that in different languages. Some languages use curly brackets. Some languages use begin and end. I mean, here we go. I mean, some languages, so C will use, those of you who used a bit of C will use something like this. They'll have, you know, print, they'll have curly brackets, right? And you can have as many, any amount of stuff inside the loop. If you're basic, if you use basic at all, anytime, you might have done for I equals 1 to 10 do, and then it would have started, something may have started, well, it depends on language, but it may have done, might have had a begin there and then maybe an end here. That's another way of grouping things. Python does it differently. Python uses indentation to indicate grouping, all right? This is a very critical thing, you know, and it's the one thing that's going to throw you off at the beginning. It doesn't matter how much you indent. I've indented 2 spaces, right? 2 spaces. I could indent 1 space, it'll still be happy, right? I can indent, you know, 100 spaces and it's still happy, all right? But 2 spaces is a convenient one. So I'll just go back 2 spaces. The whole point of indentation is to group things. So I can go print, how about we do I times I, and another one print I times I times times I times I. So those 3 prints are grouped together. If I run this, you'll see we get a lot more output. Okay, a lot more output. That's because the 3 prints are part of the loop. Sorry, part of the loop. If I were to do this, unindent, those 2 print statements are not part of the loop. Much smaller. The I it picks up here is the last I it found in the list. All right, so that's why it's 16 and 64. All right, so this is really, really important to get into your mind, the idea of indentation as a way of grouping things together. And in a loop, it's obviously natural to group a bunch of things together. Okay.
As they're putting out in the chat, you just have to have the same indentation for anything you want to get.
Ah, that's a, thank you. Yeah, that's an, yeah, don't do this. That won't work. In fact, I suspect I get a nasty error message saying unexpected indent short for indentation. Yeah, don't do that. The indentation has to be at the same level. It doesn't matter what level, so long as it's the same, okay? That's a very good point to make, all right? So let me rerun that to get rid of the error. Okay, good, thank you. This little comment here, you'll see this a number of times as we go on. It says, note the indentation to group operations inside the loop. Another easy thing to forget, don't forget the colon at the end of the first line, Okay, don't forget the colon. Here's a more elaborate version of a loop with a little calculation in there. I can run this and I get the sum out. Okay, all right. You know, like with anything, whether you're playing the piano, learning to ride a bike, or whatever, programming requires practice, and you know, you don't expect to be able to do this immediately. It will take practice before all this becomes second nature to you, but practice is critical for learning programming.
The last thing it printed out for sum is not the value that sum has going forward, because it printed it before it added it.
Whoopsie daisy, yes.
Yeah.
There it is.
Yeah.
10. That's right, yes. Yeah, and of course it's 2 prints now, so I'm getting double out as well. Yeah, these good points. Okay. All right, so I want to say now a little bit more about lists, because we use the list here. So by the way, if we want a little break, we're an hour in, and I suspect we could do with a little break. It's exactly 9 o'clock my time. Are we okay with a 5-10 minute break? Lucy, Veronica, is that okay?
Yeah, it's okay with me.
Yeah. Okay, so we can have a 10-minute break. All right, so you can go out, walk about, or do whatever you have to do. Hopefully it won't be reading emails, because that's the worst job in the world. Oh yeah.
There you go. Okay.
Thanks a lot. Yes. That's what I forget. So yeah, welcome back. So we're in the middle of loops. So we had a little interesting discussion about this little fragment here, and I changed it a little bit. By the way, I put in line numbers here now. So if you have any questions, you can refer to actually a line number. All right. So these are just line numbers. They're not part of the code. All right. Okay. So let's just go back to lists a bit then, because obviously this is, well, not obviously, but you'll recognize this piece here to be a list. Okay. And this is one reason why I introduced list early on, because you'll see them come up pretty frequently. You can do lots of things with lists. And what happens if I wanted to do a loop from, 1 to 100 rather than 1 to 4? Well, you're not going to expect me to type, 1, 2, 3, 4, 5, 6 all the way to 100, I hope. And no, most people don't expect you to do that. Instead, there's a special function called range, which constructs a list for you. And the argument is the number of entries in the list. So let's, well, it's already run, but let me run it anyway. So I create a list L using this function range. 5 are the number of elements in the list starting from 0. I then print it. Now I have to do this funny thing here, list L. This is a technical thing about. So in previous versions of Python, much older than this one, if you did, list 1,000,000, so range 1,000,000, it would literally try to give you and you try to print that out, it would literally try to print out a list with 1,000,000 elements, which, wouldn't go down well because it'd be so huge and take so long to do. So instead they changed it so that actually, if you just did L, you'll actually just get the range. It doesn't try to what's called evaluate it for this reason, because it would be too time intensive if you had a massive range. If you want to see if you wanted to evaluate the range, you have to force it to make it a list. Okay, and then you'll see it. Now, of course, this list you could use in a loop, and I've got it here. So now I've got this list here, range 10. So let's just let's see what range 10 is. So remember, the list starts from 0, gives you 10 elements. And since it starts from 0, 10 elements means it goes to 9, okay? So when you see something like 10, there are 10 elements, but they'll go from 0 to 10 minus 1, okay? You'll see this a lot because a lot of the indexing in Python starts at 0, right? So if you say you want 5 or something, you're actually getting numbers from 0 to 4, not 1 to 5 or 0 to 5. All right. Yeah. Note lists start at 0. Okay. All right, but I can use this range directly in the loop. I don't have to put, the list itself. Okay. I can do that, and this is a very common thing that people do. hold on, my screen is just frozen. Oh, there it goes again, sorry. For I equals, for I in range 10, then I have a little calculation, then I print out the sum. If I run this, you'll see it's 45, all right? So it's running through the sum, it's running through the loop, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and stops, okay? Now range, you know, can do other things. In fact, if I were to, if I get rid of this here and then just go E, and that, it comes up with a help. There's a whole bunch of things that range can do, and you might want to use Google or something to look up actually what range can do. But range can do a bunch of things. One thing, for example, you can actually specify the start number and the number of elements. Sorry, and the sorry, the start number and the final and the number of elements. Sorry, I get that straight again. The start number and the last number of the list, -1, okay? So this is one of the confusing things that sometimes you have to think, like I just did, to get it straight in your mind. But if I were to run this, range 2 to 5, it starts at 2, ends at 4, which is 1 minus 5. So that -1 matches the -1 up here, okay? So that 10 means actually ends at 9 because it starts at 0. This 5 here means actually ends at 4, but it starts at 2, right? So if I were to go something like 8, you would know that would mean it goes from 2 to 7. Hold on, it's frozen again. There, right? It goes from 7. So it goes from 2, 3, 4, 5, 6, 7. 1 minus the number you put here, right? So that's really important, right? So note the list stops one before the last value of 5, right? So that's one thing to remember. The other thing you can do is you can add a third argument, which gives you the step. So at the moment, they're going, you know, in increments of 1, 2, 3, 4, 5, 6, 7. You might want to go in increments of 2, and that's exactly what you can do by adding a third argument like that, okay? So that means you can do tricks like this. You can, for example, sum all even numbers up to 20. So I'm going every 2. Note I'm using 21 here because I want to go up to 20. So 21 is 21 minus 1. And then so I can sum all my numbers up to 20. And this is what the sum then is 110. Each case I'm printing out I. So it goes from 2, 4, 6, 8 up to 20. 1 minus the 21. Then it prints out the sum. Right,
I so the same thing would happen if you told it to go to 22 because 22,
yeah,
21 isn't on your list, right?
Yeah,
basically.
Well, it's freezing all the time. Yeah, there you
Mm-hmm.
go. If you try 22, yeah, it goes up to 20.
Yeah.
If you want to do 22, you need to go to 23. Okay. Yeah, this is potentially very confusing. The key thing to remember is that all indexing starts from 0, which is why you often have to take one off, an upper bound. Okay, so that's pretty much all you need to know about lists. Actually, with that, you can go a long way with lists. Obviously, there are more sophisticated things you can do with lists. So I'm not going to talk about some of the most sophisticated things for doing lists, but you can go a long way with just this. In fact, you can probably go 98% of the way with just these. The only thing with lists, they're a bit slow, and there are various tricks you can do to speed them up, but for our purposes, it doesn't really matter. Okay, so the next thing I want to talk about are if statements. These are, these are tests. You test something to see it's true or false, and if it's true, you do something. If it's false, you do something else. So it's a common activity in programming, of course. Pretty much every language has something like this. And the bare bones example is if true, print it's true, right? So I run this, and hey presto, I get it's true, right? Again, I'm going to use these 3 lines which I had before. Note the indentation. So I can put something else here. It's still true. All right. And it prints them both out. The indentation groups things within the if statement. Okay. The other thing to remember, again, like before, don't forget the colon at the end of the first line. Don't forget that colon, right? A lot of these things, all these statements have colons at the end. The for loop, the if statement right at the beginning, all right? Now I put a literal truth here, but of course you can put anything you like here, so long as it it represents a true or a false. So in other words, I can do something like this, a equals 6, and I can go if a is greater than 4, sorry, which it is. Oops, frozen again. There you go. That's true. If I were to say if a is greater than 7, which it isn't, I won't get anything out. Oh, in fact, here's another simple example that I did here. So let's try this. If a is greater than 3, all right. You have all the main operators: greater than, less than, greater than or equal, less than equal. This one is not equal. Exclamation mark equals. This one often gets people. This is what's called the equality test. Tests where two things are equal. You cannot use just a single equal sign to test for equality. The single equal sign is used for assigning stuff. So I'm using this single equal sign here to say that 4 is assigned to x. I cannot go if x equals 3 because that tells the computer x is assigned to 3, which is neither true or false. So if I actually were to run this, it would get upset. It says invalid syntax. If I want to check if x is 3, I need to use double equals. And this is common in a lot of languages, in fact. And it's another thing that can get people if they're not careful. Now it's happy. Okay. All right. What happens if I wanted to do the the alternative? If it's I got if a is greater than 7, what do I want to do something if it's not greater than 7, right? Then I can put an else in. Thing remember about an else, colon, and the indentation is exactly on the if. Right? This else belongs to this if. I know that because it's got the same level of indentation. Okay. You can imagine having lots of ifs nested in each other and lots of elses. You associate elses with a particular f by its indentation. Okay, so this else is associated with this if. Okay, so now I can do a print here. And before I execute it, not true, I'll put there. This print is at the same level of indentation as this. Okay. Right now, actually, come to think of it, it might accept that. It does accept it. Okay, but to make things clearer to the reader, I would make the if. Oh, it's frozen again. Hold on. I would make the if group block the same indentation as the if block. Okay. So you can see now it's not true. A is 6. A is not greater than 7. So it does the if. Okay. So a couple of things to remember: the colon, the indentation, and if you do an else, the indentation there as well. Okay. And when you do equality, use double equals, not single equals. Okay. So you can go crazy here. It's not just numbers you can work with. You can work with strings. So here I'm testing if ATP is the same as ATP, which it isn't, of course. So if I run this,
Do a
get
quick
nothing. Yeah.
elif thing.
Oh, if you want to, right. If you have a whole string of ifs, this is one of the things that bugs me about Python. There is no proper switch statement. Those of you who know other languages will have come across case statements or switch statements. We have lots of options, and you want to select the option based on some variable. In Python, they don't have that, which is a real nuisance, I think. In those cases, you can do a long string of else ifs. So let's say I want to know if S1 is ATP. Okay, so I can go. Well, I want to know what is it? Is it ATP?
I mean, you could do like S1 equals S2 is greater than or less than, maybe. Those are like three easy
I
cases.
tell you what. Yeah. Well, yes, that's a good idea. Let's do. Oops, so it's frozen again. Hold on. Come back. Here we're back again. So if I have 8 here, so I can go if S is greater than 8. S is greater than 8. I'll just put greater. All right. Else if I think it's just this.
before the colon.
What's that?
elif space S1 equals whatever for your colon above. Yeah, there you go.
All right. S1 is less than 8. I'll do 3, okay? And then print, yeah, because I don't use else if very often. Sometimes I do. That is frozen again. Hold on for a second as it unfreezes itself. There you go. Print S1 is less. And then finally, well, if it's not greater than less, then it must be equal, I guess. Then else print equal. So let's run this and see what we get. Equal. Just to make sure it works, let's do 9. Let's run that. S1 is greater, thank you very much. And if it's 6, it should print it's less. And it's less, okay? So in other languages, you do it differently. You have switch statements or case statements, but in Python, I don't know why they don't include that. It'd be a nice addition. You have to have a whole string of else ifs, okay, to do that. All right. You can go crazy. I have no idea what this does. I just made it up, but you can have any number of checks in your if expression. So I got if x is less than 5 and y is greater than 1, or z is not equal to a word, then whatever this means, it's true. All right. So I can run this, and it actually says, oh, it's frozen again. It actually says it's true. All right. So you can go crazy on the if statements. You can have any number of, ands and ors and nots and less thans and greater thans, and you can mix variable types and integers and floats and words and so on.
It might be worth pointing out that Python is case sensitive. So z indeed is not equal to a word, because a word and in your if is lowercase, right?
That's right. Yes.
Yeah.
So the other thing I should point out, if I did this, that'll also cause a problem.
Yeah.
Okay. So yeah, one thing I didn't mention, actually, that's a good point, is that Python is what's called case sensitive. A lot of languages are, some languages aren't, which can annoy normal users, because if they see this, oops, sorry, that and that, a normal person will think they're the same thing. To Python, they are not. They are completely different, because this starts with a capital G and this starts with a lowercase g. So that's an easy place where mistakes can appear. So be aware of that. Okay. And I just remind you again, don't forget the colon at the end of the if list. And there it is, right, in all its glory. Okay. Easy one to forget. Okay. All right, a little bit more about lists. Very useful. They pop up all over the place. So let's just learn a few more things about lists. I mentioned this before. You can add lists together. Okay, so I get 1, 2, 3, 4, 1, 2, 3, 4. We've seen that before. If you want to know how long a list is, you use len, short for length. Okay, so this list I made up here is called new list, and it's frozen again. Is 8. Okay, oops. Here's an interesting learning opportunity. It says new list is not defined, but hold on a minute. I have new list up here. That's because in this new session, although it looks like the answer is here, that was from a previous session. I checked it yesterday, right? I need to run this cell in order to make sure new list was created. So now it's created, all right? So that's one of the things about notebooks you have to be careful. Cells can depend on previous cells, and you have to make sure that the previous cells were executed. Okay, and I think there's something up here to say run all. Right, so if you have a big script and you just want to run every cell in the script, you can ask it to run the whole thing. Okay, so remember that. Sometimes you can get some funny bugs because you forgot to execute an earlier cell. Right, and some later cell depends on the result of some earlier cell. Okay. All right, so that's how you get the length. You can have empty lists. You may be wondering, what on earth do I want an empty list for? It doesn't seem to be very useful. It can be very handy if you're trying to build up a new list. And there's a thing called append, right, which means add to, and particularly add to the end. So I can append anything I like to a list, 1, 3.14, a string. If I print this, I get the list containing 3.14 a string. All right, so that's a very handy thing to know. So we've got adding lists, length of lists, and appending lists. Obviously, there are lots and lots of other commands that are available to lists, which I'm not going to go over. Like searching lists, deleting lists, reversing lists, all sorts of things you can do with lists. And there's a whole thing online. You can go and find out what useful things you can do with lists. But these are some of the basic things. One thing that we will need, you may end up having to do this week, is something called slicing. Now, slicing in lists also works with arrays, which we'll come to in a minute, is a way of extracting pieces from a list, okay? So you can extract sections from a list using slicing. It can be tricky to remember. You get it with practice, but these are examples of what a slice looks like. So one thing let me do something here first before we go into slice. Let me go print L0. One thing I never mentioned is lists can be indexed. So number 0 is the first item in the list, which is 1. Number 1 is the second item in the list, which is 3.14. And number 2, sorry, is the third item in the list, which is, it's just frozen again, hold on, here it comes, is a string, right? So that's the first thing I should let you know. You can index list. And these numbers refer to that indexing, right? So you've got square brackets here, I had square brackets here, right? Same thing, but the number inside has changed to what's called a slice, right? And these numbers are the index into the list. 0 is the first item, and therefore 1 is the second item. So this 1 here refers to the second item. This 5 refers to the sixth item. Okay. And let me show you the syntax here. So there are various forms for this slicing. The common one is start to stop. So this will pull out items from start through to stop -1. Okay. So, and then let's show an example here. So I got a list here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I do list 1 to 5, number 1 refers to the second item, all right, so that's a 2. And then it goes all the way up to, then it does 5 minus 1 of the items, and 5 minus 1 is 4, so it does 4 items starting from 2. So that's 1, 2, 3, 4. And so it goes, and then it outputs 2, 3, 4, 5, okay? All right. The second, I can add a second number, which is if I want to jump, jump every so many items in the list, this jumps every 2. It'll go from, starts off with the second item, and it goes up to 10 items, but jumps every 2. So I get 2, 4, 6, 8, 10. Using lists takes a bit of practice. I would definitely practice this. We might be using, slicing. We might be using this week. It's certainly handy when you get out big chunks of data and you want to be able to, extract columns, extract rows, and so on. So, so be aware of this idea of slicing. We'll be seeing it again this week, and whenever we use this slicing, I would recommend the person explain a little bit what the slicing is. Okay.
You want to go over the -1 syntax, like the -1 index, which is actually the last element?
Yeah, I wasn't going to touch that, but
okay.
But anyway, yeah, there's a lot of other stuff you can do with slicing. For example, let me see. If I go -1. So I don't use this very often, I get the last element. So it's a cute thing to do. -1 it's basically the indexing starts from the other direction, essentially.
It's mostly useful when you don't know how long the list is. It's just give me the last thing.
Oh yeah, that's true. Yeah, if you know that, yeah, that's right. Yeah, if you want the last thing, you get -2. If you want the last thing but 1, if that's frozen, hold on. Come on. There you go. I get 9. Okay, so basically it's basically reversing the it's sort of reversing the indexing, not quite. But it can be useful to grab things. So if you want this stop here, for example, if you wanted to go right to the end, you could put a -1 there, all right? And it'll then go from, if this were, start, it'll go from start all the way to the end, okay? All right. You can do things like delete items, and you can use slicing then to delete sections from it. It's pretty flexible syntax. It does take a little bit of getting used to, but it's used more and more in languages. MATLAB uses it. A lot of the new languages like Go and especially Go, they use something similar as well. Okay. As I said, you don't need to know much about lists to really use them effectively. So, but there's a whole bunch of clever things you can do with lists. We'll move on to the next one, user-defined functions. I won't dwell too much on this because this is pretty straightforward. It's often the case that you want to package things up into functions, maybe because you're reusing this function in many places, or you just want to divide up your program into more, manageable parts, which make more sense to you. And it's really easy to define a function. Here I've got a function called myfunc, and myfunction, which just adds up 2 numbers. You start off with the keyword def for definition. You add the name of the function. These are what's called the arguments. These are the things you want to pass into the function. And then that old famous colon you must put at the end. And then again, you need the indentation to indicate this is part of the function. And if you want to return something from the function, you use return x, okay? And again, I repeat this thing here. Note the indentation, note the colon, all right? So let me run this cell. By the way, again, let me show you this. If I don't run this cell and I try to run this cell down here, which uses the function, it says, I've never heard of my function. What are you talking about? That's because I need to run this first to get my function into Python's memory. Then it just ran, took a while, and then I can run it, and now I get the answer back, which is the number 5. 2 plus 3. Okay. All right. There's a question on Slack about dictionaries. I'm not going to touch dictionaries this morning, but we may come to them. What we'll do is, as we need dictionaries later on in the week, we'll introduce dictionaries at that point. The reason for not introducing dictionary now is because you'll get information overload. It's better to just do the basic stuff now, and then dictionaries, which are a really nice feature of Python, will come to when you need them. Okay. Plotting. Everybody loves plotting. That's not it. Sorry. Everybody loves to plot. So, we'll be doing a lot of plotting, and this is one reason why you want to get yourself a fancy interface to Python, because plotting requires producing a visual image, and the raw Python interface you get for python.org can't do that, as far as I know. I don't think it can. So that's one reason you want one of these fancy interfaces, either Spider, PyCharm, Visual Studio Code, or in this case, Jupyter Notebooks, so you can actually get the plots to appear on the screen. Okay. So let's do it. So this is an example of a really long import statement, and it's one I always forget for some reason. So I always keep it handy so I can just cut and paste. But I have to import the plotting library. It's a bit of a mouthful. It's called matplotlib.pyplot. And the last thing you want to do is have to type that all the time. So what people often do is they shorten it to plut. Okay, so it's import matplotlib.pyplot as plut. All right. So I'm going to be using plut everywhere, and you'll notice that if you go online and search things, a lot of people use plut for the plotting. All right. So this is where as becomes really handy. So let's do some plotting. It's actually really easy. I'm going to plot x versus y. Here, 2 lists. First list is x, second list is y. I go just plot, and I hit the run button, and oops, notice this is again an example where I need to make sure the previous cell is executed first, and now I can go plot it, and I get a nice plot. All right. Why don't we do something a bit more interesting than that? Let's generate some random data and we'll plot that. Now, this is where we introduce another extremely important library. The two most important libraries we'll be using this week is the plotting library, this matplotlib, and an array library called NumPy. NumPy is used everywhere. Okay, it's funny that Python doesn't have very good array support, for handling arrays of numbers. Lists are not quite like arrays because lists can contain any kind of data type you want. But arrays are specifically designed to hold one particular data type. And the minute the computer program knows that an array contains one particular data type, it can do all sorts of clever optimizations on it to make things go faster. And of course, once you have an array of numbers, for example, you can start representing matrices and vectors. And then you can do all sorts of clever things then with those. So NumPy is critically important to Python. And again, what people tend to do is they shorten NumPy to NP. Okay, so they take NumPy and shorten to NP. Very common. And NumPy is a big package with lots of useful things. And one thing I want to show you here is the ability to generate a random vector of numbers. And so, it's a function. It's a library for working with arrays of numbers. There's lots of functions for creating arrays. One of those is to create random numbers. And this line here will let me create a vector of 1 of 10 random numbers drawn from a uniform distribution between 0 and 1. Okay. So if I run this, I run it. Oh, yeah, I gotta make sure I gotta load in NumPy. Load in NumPy. There it goes. Now I can run the random number generator, and I get 10 random numbers. Okay. There's another function on NumPy called arange. It's similar to arange, but it's for NumPy. This will generate an array. This generates an array. Let's see what it actually does first, shall we? Let's move this up to here. Oops, it's frozen again. Hold on for a second. Oops. Come on. No, it's just waiting. There it goes. So let me move this up to here just to show you what it produces. Okay, I'll put it into there then. Okay, run that, and then ask it for what x is. Print x. I get 100 numbers between 0 and 99. Okay, so this is a quick way of producing a bunch of numbers. I can produce floating point numbers this way as well. I can skip as well. So arange is pretty flexible. So I'm now generating 2 arrays, x and y, and then I'm going to plot x and y. Note that up here, oh, it's frozen again. I gave matplotlib lists. Matplotlib also accepts NumPy arrays, which is very handy. So let me run this, and I get myself a random plot. Every time I do it, I'll get a slightly different plot because each time I'm generating different random numbers for y. Okay. All right. So you're saying, yeah, but hold on a minute. I really don't like this blue color. I'm really against blue. I'd like a different color. I want red. So to do that, it's actually quite simple. You just add another argument. You can actually either spell out red, or you can type the just a single letter R, and I get a red one. And you say, hold on a minute, no, there's something else I don't like. I want to actually see the points in this plot. You can do that by indicating a marker symbol. There are lots of different marker symbols. I'm going to use the round. So let's run that. Oh, there you go. You think, yeah, hold on a minute. I don't like the fact that the markers are red and the line is red as well. I want a different color. Okay, so I'll add another option. Marker face color blue. Okay, so once I'm unfrozen, I'll run this. Google obviously is straining this morning. Then we do that. I got some blue points, but hold on a minute. The edge color is still red. I don't want that. So marker edge color, I'll set that to blue as well. Okay, now I finally have something I want. Okay. So the plot command is a bit like that. You can just add all these options, you know, to tailor make your plot. So in this case, I changed some colors and things like that.
It might be worth pointing out the fact that some of these arguments are positional and some are by name. Just that's a thing that Python likes to do a lot.
That's true. Yes, in fact, I've not mentioned that at all. That's a very good point. So there are two types of argument in Python: named ones and unnamed ones. Unnamed ones always have to come first. Okay, and they have to be in the right order. So the first unnamed one for a plot is always the x-axis. The second one is always the y-axis. And presumably the third one is always the color, I guess, if I'm right. Now, after that, there are these named ones, okay? Now, it doesn't know, if you just type blue here, it doesn't actually know whether you mean the line should be blue, or the marker should be blue, or the outline of the marker should be blue. So you can be much more precise by actually using a named argument, and this is where these names come in. So I'm specifically saying here, the marker face color should be blue. The marker here should be a little O, and the marker edge color should be blue. You'll be seeing this a lot in the next few days, right? Where sometimes the arguments are unnamed. That's because we know what the order should be, and they're at the beginning of the call. And there are a bunch of others which are optional, but we need to be specific about what they are. And they can come in any order you like, right? Because I could put marker at the end. It doesn't matter because it's named, right? So named arguments can come in any order, except they have to always come after the unnamed ones. Yeah, so you'll see this a lot. Okay. If there's anything else I should add there, Lucian.
It seems reasonable.
Yeah. Okay. And now you're saying, yeah, but hold on a minute. I can't publish this. It hasn't got a title. It hasn't got labeling. I really need labeling. Okay, let's add some labeling then. I'll add an X label. I'll add a Y label, and I'll add a main title. There we go. Write the paper, publish now. We can publish that. Okay. You're maybe wondering, but how do I get this into my paper? Well, a quick way is just to go copy image or save image. You right click over the image. You can grab hold of the image and get it. There are other clever things you can do. You might want this actually as a PDF, which will be more, which you can scale up and down. And there's a thing called save fig after this, which you can then save it as a PDF. Okay. But you're saying, now the other thing you're saying, yes, but my plots have more than one data set, right? You know, I don't have one kind of data. So, but it's actually pretty straightforward. If you want to plot lots of data sets, you can just add more and more plots. You just keep adding more and more plots, and those plots get added onto the existing plot. You might be saying that, yeah, hold on though, how do I then move on to a new plot if it just keeps adding to the existing plot? In the notebook, you get away with it because a single cell represents a single plot. In something we have one long script and many plots, what you'd have to do is to finish off a plot, you have to go plot.show. And then any subsequent plots will create a new plot. Now, you don't have to do that with the notebook because the end of the cell basically much calls a show for you. But if you're not using a notebook, you want to use plot.show to say this is the end of the plot. Okay. All right, but we don't have to in the notebook because it does it implicitly. Here's a more complicated one where we have now two plots, and I'm plotting linear, quadratic, and cubic. This is something else that's very interesting about NumPy. NumPy calculations can be vectorized, and by that I mean I'm producing a vector x from 0 to 2. With 100 points, so that means it's probably 0.01, 0.02, 0.03, something like that. In fact, let me run this and then print out what x is, okay? Just to show you what that is. X is, yeah, so this is x. Oh, yeah, it's 0.02. It's not going up in evens of 0.01 because of this. If I did 101, it would then probably be even. There you go. So it's going at 0.02, 0.04, and so on up to 2. Okay. So this is a way of producing another one called lint space for producing a vector of numbers like this. Nice thing about NumPy is if I go x to the power of 2, it knows that x is a vector, and it'll square every element in the vector. The same goes for x to the power of 3. It'll cube every element in the vector. So this is an example of NumPy being used to do vector operations. Very concise, very useful at times. I don't have to write a loop or anything, to loop through to calculate every element of the y-axis. I just have to do this. So I've got 3 plots here, 2 labels, 3 labels, sorry, plus the title. And then I'm doing a legend because I need a legend because I got 3 plots. And I can mark each plot with a label. So this is another named argument called label. This basically labels the plot: linear, quadratic, cubic. When I run this, I get a plot like this. Okay. So you see my linear, square, and cubic, and then I have the legend there. Okay. Just here's a list of colors for you for your convenience. There's a list of markers you can have here. The little circles that I use, and I can use squares and crosses and all sorts of things. This is where I point out, strictly speaking, we should call show. You don't have to do a notebook because it's implicit, but if you're doing some other platform like Spider, PyCharm, and so on, excuse me, you'll have to put the show explicitly. Okay. All right, I found there are lots of useful tutorials here, all right, for working with Matplotlib. You can do a lot of stuff with Matplotlib, lots and lots of things, which we don't have time to go over, but you've got the basics now. You can do a lot with the basics. I think we're coming to the end of this. A little bit more on NumPy. This is the library NumPy, which we're going to shorten to NP. Just briefly, some things you can do with NumPy. This is how you can create a NumPy array from a list of numbers. Okay, that's all that does. Here I'm creating a 2D array, which is basically a matrix. Okay, and I can do this by using a nested list like that. I can have any dimensions I want, like n-dimensional array. I can have as many dimensions within the dimensions. Here I've got a 2 by 5. Which begs the question, how do I know how many dimensions does an array have, and what is the shape? Is it a 2 by 2, 2 by 3, 4 by 5? What is it? I basically want to know the number of rows and columns. So ndim is the number of dimensions. For this array here, m, it's 2. The shape comes back as this funny little bracketed thing. This tells me it's a 2 by 5. Technically, this thing is called a tuple. It's just a list of I won't use the word list, but a sequence of numbers.
It's basically a list you can't change.
Yeah, right. It's basically a list that you can't change. I don't use them much myself, but some libraries use them, and in this case, NumPy uses them to return the shape. And I can get hat if I go. I can get in an individual dimension by going shape 0. Oh, hold on, sorry. Math. Oh, yes, sorry. It's remembering something previously, so I need to make sure I execute all these cells. And then, okay, so shape 0, index 0 gives me the dimension of the first dimension, which is the number of rows. Second one is the number of columns. I can produce matrices just containing all zeros. I can produce matrices containing all ones. That's a 5 by 5. There's 3 by 4. I can produce a random matrix, 4 by 4. My random matrix. Let's do that here. Let's run this. And you see what I've got here. I've got a 3 by 4 0 matrix. I got a 5 by 5 1 matrix, and I got a 4 by 4 matrix of random numbers. We've seen lint space before. That's for producing an array which has a specific set of numbers in it and size. Hold on, it's paused. paused. Hold on. Because yeah, and then here I'm showing you this feature where you can do vector operations, which is really useful. So I'm producing a vector of numbers ranging from 0 to 2 pi. All right, and then I'm using numpy.signv to apply that vector to sine so that it computes a vector f containing sine values based on the vector v. So and then I'm going to print out f, and then I'm going to plot v versus f, and you'll see what happens once it's stopped pausing. There it goes. There's the sine values. Then I plotted it. So this is a nice convenient way of doing plots by using the vector operations in NumPy. I can do slicing. So I'm not going to go over this for the reasons of time, but the same slicing we did with lists is the same here with arrays. Okay. One useful thing that we might have to do is to pull out columns. Let's say you had a whole bunch of columns and you wanted to plot, the second column versus the fifth column. You can use slicing to pull those columns out. The only thing you have to remember is the syntax is a little bit more elaborate here. We have something, comma, something. The first thing refers to the rows, the second thing to the columns. So what this thing means, with all rows, pull out the first column. All right. So this is my M here. If I pull out the first column, so the first column, of course, is, sorry, it's frozen. First column is, once it unfreezes, well, is this first piece here, 0.47, 0.25, 0.79, and here I have it here. Okay, pulls out the first column. If I wanted to extract columns 1 and 2, okay, remember the indexing starts from 0, so this will avoid the first column. All rows, but columns 1 to 2. Remember, I have to subtract 1 from the 3. I get the 2 middle columns here from 0.93, 0.37 down. Okay, so we might end up having to do something like this later in the week. So this is something to be aware of. The array package has a lot of basic array manipulation, like doing the transpose. I don't know if we will be able to be using that, but you can take the transpose of an array and things like that. So what I'm going to do now is I'm going to stop there. We're going to take a 5-minute break. Then I want to briefly come back to importing data. This won't take long. And that'll be the end then of the Python introduction. I know you have to absorb, those of you who didn't know Python have to absorb a lot. Those of you who knew Python probably thinking, why do I have to go through this? We've finished now on that, except for this little bit about importing data, which I want to talk about because it's something you may need for the rest of the week. So let's take a 5-minute break. We'll come back. Well, let's come back at 9:05, okay? 5 past the hour, sorry, 10 my time, but 5 past the hour your time. And we'll talk about importing data. But we'll have, thank you. The recording has started. So sorry, that was a short break, but now we'll have a much bigger break. So I just want to briefly touch on importing data. If you go to the session 1 for day 1, you'll see there's a data file here, okay, data1.csv. This is a copper separated value file. If I double click on it, you'll see what it looks like. It's just 3 columns of data, okay, and I've labeled time A and B, and they go up to 20. I'd like to use this data. Actually, I'd like to plot this data. So how do I get this data from here into Colab? There are different ways to do this, and I'm going to show you one way. This is just one way, and other people may show you other ways to do it in the week, but this is one way. What you can do is you can right-click, download it to your local machine. So it's already downloaded there, right? So I'm not going to download it again, but there is data1 CSV. I'm not going to download it again. Let's pretend I've downloaded it. So I've downloaded it. I go back to the notebook, and then I import this thing called Google Colab. Okay, I'm using a funky looking import statement here. This is basically pulling out this library. Colab contains other sort of sub libraries, and I'm pulling out a sub library from this called files, and this is the syntax I need to use to do that. So from this library, I want to import this other thing in the library. Okay, so you need to import that. Then this is only for Colab. Okay, this is only for this notebook. Then I'm going to use this thing called upload or files upload. So I'm going to run this. I'm going to run this cell. Okay, when you run this cell, a little thing called a widget appears in the bottom. And in the bottom here, it has a thing called choose files or cancel upload. I'm going to go choose files. And what this does is it lets me import a file from my local machine. And the file I'm going to upload is data. And the reason we have to do this is because I'm downloading it from my Google Drive and then re-uploading it to the notebook. That's basically what I'm doing. So I'm going to open this. Okay, and there it goes. It just uploaded it. It's now in my local notebook area. Okay, I have now access to it. So what I'm going to do now is I'm going to use this little script here. This is going to load that data. So I'm going to use NumPy. NumPy has very powerful methods for loading data and saving data. I'm going to import NumPy. Again, I'm going to use the shortcut MP. And MP has this thing called gen from text. Basically, it'll generate a NumPy array from a text file. The text file is given is the name data1.csv. I have to tell it that what the separating character is between the data columns, which is a comma. All right, so if I go back here, let me just show you. I double click on my data. Oh, well, you don't actually see it here, but I can show you. Well, it's called CSV, comma separated values. There are commas separating these values. All right, so I have to tell it that. The other options are possibly you might have spaces separating the values, or you may even have tabs separating the values. So you can say that here. And then the other thing I'm telling it, there are names at the beginning of the columns. So those names these are just strings. They're time, A, and B. So I'm telling it there are names at the beginning of the columns. All right, so if I run this and then print out the NumPy array, it actually shows you the data I read in, right? It doesn't show you the columns names, but the column names are there. The really useful thing about column names is you don't have to use that complicated looking splicing. You can actually literally use the name of the column. All right, that's the great advantage here. So I'm actually going to tell it, print out the column name time, print out the column name A. If I do that, I get the two columns A and B. Oh, sorry, time and A. All right. Now, what's really nice, I can now plot them. And it's really easy. Once they're named like this, it's really easy to plot because you don't need to use any of this slicing syntax. I can just say plot time against A, plot time against B. And I run that. Right, once it unfreezes itself. Yeah, wait for it to unfreeze. There it goes. And I get my two plots. All right, so that's a very simple way of getting hold of data and plotting it. If your data is a proper CSV file with headings, those headings, it becomes really easy then to do the plotting. And we might probably be, I think we'd be doing some of this this week because Roadrunner, our Tellurium simulation engine, returns data in this form. All right, it returns a NumPy array with all the columns labeled. So it's very easy then to plot data that's generated by our simulator. Okay, that is the end of that. It's a very fast introduction to Python. Obviously, Python there's a lot more to Python than this, but I think you've got the basics. If you have time, you can go over this intro again, just to check that you know things and use it as a reference. But hopefully you'll have some practice this week in exercising some of the things you've learned there, okay? So there's some good questions and answers coming up in chat. Somebody points out there's a CSV library. Absolutely. That's a good point. Python is very rich in libraries. As I said, there's probably tens of thousands of libraries available that you can get hold of. You can pretty much do anything you want if you have a, if you can do enough research to figure out how to do it. But these are some of the basics. Okay. All right. So what are we going to do now? We're going to start the modeling section. I'm going to do a bit of theory. I know you haven't had a chance to do any exercises, but don't worry. For the rest of the week, there will be exercises for you to do. This morning happened to be a bit on the long side, on the lecture side, but that just was unavoidable to get you started. So now I'm going to switch over to a more traditional lecture. Let me I guess I should download this. Actually, no, what I'll do is, I've got it here. In fact, let me grab hold of it here. Oops, let me grab hold of it here. Here we go. It's on the other side of my screen. Here we go. And then I think, I can't remember if I have a presentation mode or not, but anyway, here we go. So this is a presentation I have. I have the LaTeX. This is done in LaTeX, which I can copy that into the Google Drive if you want. The PowerPoint, there are PowerPoints as well. I have no restriction on what you can do with these PowerPoints and LaTeX files. So if you want to use them in your own classes, etc., feel free to do so. So what I want to start now is a sort of introduction to modeling cellular networks. Veronica is going to do more this afternoon. I'm just going to get you started here. So let's begin. So I want to begin by just talking a little bit about models. It's surprising a lot of people have some misconception of models. The general public in particular really doesn't quite know what a model is. A lot of people seem to think a model of something is the truth, when of course it isn't. It isn't meant to represent the truth, but it's meant to represent our best interpretation of the data. So a really nice one, of course, is the observation of the sun and moon, not the mood. Sorry, there's a typo there. That's the moon.
We're seeing the zoom black bars on your screen for some reason. I don't know why.
Black bars.
Like your controls or your.
You're not seeing the. Let me stop.
When we see your correct screen, but we're also seeing like where the zoom controls would be is just a black bar.
What are you seeing now?
It's the same. Oh, there. Okay, now they're gone.
Oh yeah.
Yep.
Okay. For some reason they were. Yeah. Okay. Good. Yes, that should be moon. I think it's corrected in the one on the upload. Probably should use that one actually. But anyway, yeah, really nice model. Of course, is the sun, moon, and who rotates around who. And of course, the initial models suggested that the sun revolved around the Earth. That was one model. That was the best model at the time based on the data, and it seemed pretty obvious. Of course, if you look outside, the sun really seems to go around the Earth. I mean, who could argue with that? But it turned out that the model had to become really complex to explain then all the other motions in the solar system. And of course, then the model was replaced then in the 16th century by the Copernican model, where now we realize the Earth goes around the sun. So models can be definitely wrong. They usually are. But they're there to try to represent our best interpretation of the available data. Okay. They're not meant to represent the truth, just what we think is the best interpretation of the data. So we're not making any attempt to suggest that we're getting at the truth. Maybe we will one day. I mean, I think the fact that the Earth goes around the sun, I think pretty much nobody disputes that now. And maybe that well could be the reality. But in general, we don't assume that. because another model could come along and say, well, actually, we're orbiting Pluto, not the sun, but I doubt if that's going to be the case. But anyway, of course, another one is the germ theory of disease that has resulted in infection. Before that, there were other models. Like one model was that the disease was due to bad air. And so if you didn't breathe the bad air, you didn't get the infection. That also seemed to match the data they had at the time, but then people realized that you could get infection just by touching people without going through the air. So, okay, they had to modify the model. So you can see that models evolve all the time through time. As more data becomes available, old models go and new models get replaced. And it's exactly the same with the models that we might build in cellular models. So if you're building a metabolic model or a signaling model, these are not necessarily the truths. They just represent what we know at present according to the data we have. Okay. And there's a famous quotation from, is it George Bell, who said that, all models are wrong, but some are more useful than others. And that's a very true statement. Right? I still see people thinking that, a theory or a model is the actual truth of something. It's not. Right? It's just the best we have at the moment. So just because your model doesn't, if you build a model and it does some things right and some things wrong, doesn't mean it's a bad model. The things it gets right are useful. Now, the things you get wrong are not so useful, although they do tell you there's something wrong with your model, and maybe at a later date you can improve the model and fix those as well. All right. So a model doesn't have to be perfect in all aspects. It just has to be good at the things that matter to you. All right. So to a clinician, it only matters that that a model predicts a correct drug therapy, even if some of the underlying things it predicts aren't so correct. Now, models can come in all sorts of form. I've been talking to you. I've been talking to you, so they can be verbal models. You can write about models. You can describe the Earth rotating around the sun, orbiting the sun. You can describe the germ theory. You can use pictures, and the pictures is probably the most common model we see in biology by far. You look at any biochemistry textbook, full of pictures. Every one of those pictures is a model. Okay. Now you can go a lot more sophisticated. You can have mathematical equations, which is what we're going to be interested in, or you can have just computer algorithms that can actually represent some system as well. So why are models useful to us? Why not just have the data? Why do we have to have a model? Well, they help organize your data. That's probably their primary role, is to organize observations and thoughts into some organized fashion. They're a good way of transmitting your thoughts to a colleague. I could collect data on something and I could just pass the data to somebody else, but how's that going to help them? But if I passed a model of that data, they'll get some insight into the data and what I was thinking about that data. Because the big thing, which is, what people like the NIH, National Institute of Health, and all the health agencies and the medical community are after, can models predict the future? Can they predict, new drug therapies? And we've seen, during COVID, of course, a lot of models attempting to predict infection rates, mortality rates, and so on. Those are crucial, of course, to policymakers in government, so they can say, well, how many, masks do we need to order? How much vaccine do we need to make, and so on. And because engineers use models all the time to predict things from spaceships to bridges. So models have lots of useful purposes. So here's a picture of a model of a model in picture. This is the water cycle. No, it's not the water cycle. It's the cycle of various chemicals in the atmosphere, including oxygen, sulfur, and so on. So we have picture models. Here's a picture model, perhaps we're all familiar with. This is the binding of substrate to enzyme to form enzyme substrate complex. This is the kind of picture I mean that you'll find in the textbooks, thousands of them like this, because these have been generated from years and years and years of study, collecting data and so on. I can turn this into a textual description. So as a more text model, I can say substrate binds to enzyme active substrate, active site, form, enzyme substrate complex, and so on. I can describe that in those terms. What we really want to do, though, is talk about mathematical models, okay? And mathematical models are a relatively new thing, at least for a lot of people in biology, although there was always a community that used mathematical models. Why use mathematical models? Well, first of all, of course, mathematics is precise. Pictures are not so precise. Text is definitely not precise, unless you make a huge effort at it. But mathematics is precise. We can formulate our ideas and identify the underlying assumptions. Mathematics is a great reasoning system. I can reason with mathematics. There are well-defined rules for doing logical operations. So it's a very good reasoning tool. It's quantitative. So I can do work with numbers and with mathematics. And of course, computers understand mathematics very well. And so once we have a mathematical model, we can include it in the computer and it will run a computer simulation. Right, so many of you probably know this already, but I just want to lay this out at the beginning so we're all starting at the same place. Lots of different kinds of mathematical models. We're going to deal with, I should have spelled this out, we're going to deal with differential equation models. So things like dx by dt equals something, but you can see there are lots of other different kinds of models that you can make. And each model is used depending on the application you have in mind. So let's look at a specific model. I'm going to make this already one that perhaps we can all appreciate. A couple of water tanks. I have a tank. I have two tanks. Tank 1, where water is coming in at a rate Q1. Do I have I don't think I have a cursor here, do I? Do I have a cursor pointer here?
Yeah, we can see your mouse.
You can see the mouse? Okay, good.
Yeah.
So I have a tank here. I have a second tank here. Water flows into the first tank at a rate Q2. Water leaves the first tank at a rate Q3, enters the second tank. Water leaves the second tank Q3. I also have another pipe coming in that brings water into tank 2. I have the height of each tank. That's the height of the water. And I have some constant K1 and K2 that somehow determines how fast the water leaves each tank. So what are our objectives here? We want to make quantitative predictions on the height of water in both tanks. We can't do that with just a picture. I can't tell you what the water in tank 2, I can probably tell you whether it's going to go up or down, but I can't tell you by how much it'll go up and by how much it'll go down. And so in order to do that, I need to convert this picture into a mathematical model. Okay. So one of the things we have to do always when doing a model, we have to make some assumptions. We're always doing that. Often the art of modeling is the art of picking the right assumptions. There are some obvious assumptions we're going to make here, and they're quite reasonable. Mass is conserved as it moves from tank to tank. What that means that these tanks are not leaking, and there isn't a little, fairy or pixie or goblin coming in and sucking out the water that I don't know about. So there's conservation of mass in terms of water. The external environment is constant. For example, the temperature here is constant. So the water is not expanding or contracting because of temperature changes. All right, that would mess up the heights, of course. So I'm assuming the external environment is constant. And I'm going to assume some laws about how the flow of water leaves the tanks. There are various things I could do here. For example, I could just assume that the rate of water flowing out of the tank is directly proportional to the height. Now that sometimes works, especially when the height isn't very high. As the height gets higher, and if the water rate goes up, you start getting that simple law breaks down. And so there's another law that was discovered some centuries ago called Torrielli's law, which shows that, interestingly, that the flow is proportional to the height of the water in the tank. So it's not proportional to the height, but to the square root of the height of the tank. And then I have this constant that just then scales that and makes the units work. Okay, and these constants here, K, are these K1 and K2. So these are the assumptions I'm going to do. I'm going to make some assumptions about the physics. I'm going to make some assumptions about the environment. And I'm going to make some assumptions about the processes and the laws by which those processes follow. Okay. With that, I'm now going to identify the different kinds of quantities that are in this system. We have the parameters. such as the Ks, and we have the diameters of the tanks. I haven't talked about the dimensions of the tank, but they have a diameter. I'm going to assume they're round, not square or any funny shape like that. So I have these parameters. These parameters in principle are modifiable, but I'm going to assume they're constant. There are the variables or the state variables which go up and down as the tank fills and empties. That's the height of the water in the tanks. Then I have something called the inputs, which are the flows of water into the tank. In this tank model, there are two inputs. This one, Q1, because I could control the amount of water coming in, and Q4, which is something I could also control the amount of water flowing in. Q2 is not an input because that is determined by tank 1. All right. So if I've got two state variables, I got height 1, height 2, I'm going to have two differential equations. Okay. So let's write down those two differential equations. The two differential equations.
You want to just quickly define what a state variable is? You could.
Oh yeah.
Okay. Yeah.
So a state variable is are those variables in the system that change as a result of the system. I distinguish them from the inputs. So the inputs are things that I control directly. And the things I control directly is the amount of water coming in, Q1, and the amount of water coming in, Q4. The things I observe or I measure is the height of water in H1 and the height of water H2. I have no direct control over H1 and H2. I only have control over Q1 and Q4. So those things which I don't have direct control, but which change over time, I will call the state variables. And there are two of them, H1 and H2. Since there are two state variables, I will assign one differential equation to each state variable. There will therefore be two differential equations. These two differential equations are these. V now is the volume of tank 1. V2 is the volume of tank 2. The change in the volume of water in every tank must be equal to the amount of water coming in minus the flow of water out. So the flow of water in is Q1, and the flow of water out of tank 1 is Q2. So if we look at tank 1, the amount of water coming in is Q1, the amount of water leaving is Q2, sorry. I haven't said much about the units, but the units for these flows will be something like volume per unit time, all right? Liters per second, gallons per minute, whatever your favorite units are. The change in the volume in tank 2 involves three things: the amount of water coming in, Q2, Q4, and the amount of water leaving, Q3. So I'll have three terms in dV du by dt. So Q2 plus Q4 minus Q3. So these are my two differential equations that I'm going to use to model the water tank. Now on their own, they're not very useful. I saw a question. I'll come back to K1 and K2 in a minute. On their own, they're not very useful because I'm actually interested in heights, not volumes. Now, I know that if my tank is cylindrical, I know that the volume of the tank of the water is the cross-sectional area times the height, okay? So if I differentiate this expression, I get dVt equals A by dH by dt. So I now have a relationship between the rate of change of the volume and the rate of change of the height. It does involve the area, but that's fine. I don't mind about that. So what I'll do is, wherever I see dV by dt, I'll swap in a dH by dt. And then I'll divide both sides by A to move A onto the other side. If I do that, okay, this is what I'm doing here. Say with the first one, the first equation was dV1 by dt equals Q1 minus Q2. I'll swap this dV1 by dt, and I'll put in A times dH1 by dt. Then I'll divide both sides by A. And if I do that, I get this. So this is my equation for height 1. All right. I will do exactly the same thing for V2. So I'll have a dH2 by dt. All right. These are the two equations. Now, before I jump to that, note I've got Q1 here. Q1 was an input. I control that. I set that. Okay. Q2, however, is determined by the tank, because that's the outflow from the tank, and that's determined by the height of water. And remember that, I'm going to go back here, that the flow out of the tank was some constant times the square root of the height of the tank. Right? Now this K here corresponds to K1 and K2 in each tank. So when I come to Q2, I'm going to replace it with K1 times the square root of the height of H1. So that's what I've got here, okay? So this is now the final model, in fact. So I've replaced, so Q1 and Q4 are the two flows I control, and these two, or these three here, are the Qs, the Q2 and Q4, that represent the flow out of the constant, okay? Now the K1 and K2 are constants. They're somehow determined by the size of the pipe that leaves the tank. I don't know what that function is, but we could measure that empirically, experimentally. We could get the value of K1 and K2. Anyway, this is my model. Now, what do I do with this model? Well, I could solve it analytically. I could load it into Mathematica and hope it could solve it. That won't be a pretty sight because of the square roots. So it's actually rather easier just to solve them numerically. How do we do that? Well, these are differential equations, and Python has lots of support for solving differential equations. So let me just show you that. Okay, let me just show you that. First thing I have to do is type this model into Python and turn it into a function, a user function. And that's what this piece here. So this is a bit of Python code. That's what this piece does here. All right. I'm importing a whole load of stuff up here. I'm importing NumPy, we've seen before. I'm importing the matplotlib to do some plotting. I'm importing math. I need math because I got to have a square root from the flow out of the tank. And I'm doing this funny thing here, which is another important library called SciPy. And this contains lots of numerical techniques, including numerical integration. And so I need that. I'm not going to go into much detail here because I don't want to focus on this, but this piece here initializes the constants, K1 and K2, initializes the flow in, Q1 and Q4, and then writes out the two differential equations. Those two differential equations are just these two written out in Python, okay? I'm assuming the area is 1, so I don't have to divide by the area, but I end up with dh1 dt, dh2 dt. Now, what the integrate method wants is to return the rates of change as a list. So I return these two rates of change as a list, okay? It has a particular requirement for the signature for the model function, YT. We're not going to be doing this again, so I don't want to go into the detail on this. You can look this up and find out more about this. But this is basically the function that represents the model. I now want to solve this model. So I have to do three things. I have to initialize the initial condition, and initial conditions are the heights. So I'm going to assume that the two tanks are empty. I then need to define my x-axis for the time variable, which I'm using NumPy and linspace. And then I solve it. That's literally it. Okay. I use this thing called ODEInt, which comes from SciPy. It needs the model, which I've got up here. It needs the initial conditions, and it needs the time variable. And that's it. What comes back then are the solutions. And I just plot the solutions. I plot y1, which is the height h1. I plot the h2. And I add some titles, y label and y label and the legend. And then I show it. Okay. If I do that, I get this. All right, so that's the simple model of two tanks. Let me just flick forward. Okay, what is the take-home message from this exercise? Okay, let me go back and get this take-home message. First of all, we'll often have a picture, right, of something we want to model. A picture is not good enough for that because we can't really make good predictions with just a picture. You can make some, but they're not that great. We need to define our assumptions. Right, so we have a picture, define some assumptions. These assumptions include things like conservation of mass, external environments constant. I have some processes I need to define how they work. In this case, it was the flow of water out of the tank. I then need to sort out what are my parameters, my inputs, my state variables. The state variables become the differential equations. The inputs are things I control. I can change if I want. The parameters are usually things I don't change. So the diameter of the tank, excuse me. I mean, I'm not going to change the diameter of the tank. I mean, I have to make a whole new tank, right? So I'm not going to do that. I mean,
people have a few questions about just what K was and stuff. Like K is basically determined by the diameter of the outflow pipe. Is that right?
Yeah, it's something to do with the outflow pipe. I mean, this is an empirical thing. I don't know what actually determines K, but it's something to do with the outflow pipe. If the pipe is very wide, presumably K will be big. If I only have a tiny, tiny, tiny little pipe coming out, K will be small. Experimentally, I'd have to determine this. I'd have to determine this experimentally by taking a tank to one side and doing various experiments with the height and measuring the flow and trying to figure out what K is, okay? All right. Any other questions? Oh, there's one here. What was the numerical method used? That's a good question. I'm not sure what the default was. You'd have to look that up. I can't remember what the default is for ODE.
But you can set it also, though.
You can set it, though, yeah. It's either Runge Cutter 4 or Runge Cutter 45, probably. But you'd have to check the documentation for that. Is it possible to use time-varying parameters? Yes, it is. That's one reason why it feeds time into the, why time has to be there. You notice I don't actually use time at all here. But if I did have a time-varying input, like in Q1, that's where time would come in. Yeah, the gravity is wrapped into the K times square root of height. That's correct, yeah. Yeah, I don't want to dwell on this too much because we won't be doing any of this. I just wanted to show you how you would do it if you wanted to do it, the old-fashioned way, where you have to derive the differential equations yourself and then write out the script yourself and so on. But the main take-home messages are: we start with a picture, we come up with some assumptions, we make sure we know what our parameters are, our state variables and our inputs, and then we build a model. And then we find some piece of software to run the model, right? That's basically the take-home message. So what would be the equivalent of this in a cellular model? Okay, so this is where we now start on the cellular model. So what we deal with in cellular models, we deal with, and let me do a search here, metabolic pathway. For example, if I type metabolic pathway in Google and go to images, I get lots of pictures of metabolic pathways. Here we go. There's one. Well, that's not coming up very quickly. Let's try this one. That's always a famous one. Not going to come. Yeah, okay, wants me to sign in. Forget that. How about this one? Have we got one here now? Okay, that hasn't. That's not very good. Oh, here we go. Maybe you can see this one. This is a metabolic map. You can see some things you might recognize, like pyruvate, glycerate. I don't know if you see glucose anywhere. But, these things are full of chemical reactions. One compound getting converted to another. The same thing happens in protein signaling networks, in gene regulatory networks. Basically, life is one big pot of chemistry. And somehow in our models, we've got to represent this kind of thing, all right? So we need to understand how to represent, say, a single reaction. So let me go back to my slides. So here we have a single reaction. It's a generalized one. I have any number of reactants being converted to any number of products, okay? Actually, there's a mistake there, I see. I'll come back to that in a minute. These little letters in front are the stoichiometries. So I could have, one or more A's combining with one or more B's, giving one or more P's and one or more Q's, all right? Just like the water tank, in the water tank, we had to ask what determines the flow of water out of the tank. Here, I want to know what determines the rate of reaction. Often we use mass action kinetics. So there's a little mistake here, actually. There should be that plus should be a minus. I'll have to correct that. But let me show you first with this simple one. I have a simple reaction. A gets converted to B. The simplest assumption I can make is that that reaction rate is simply proportional to the concentration of A, right? So if I double A, I double the reaction rate. And K1 is the rate constant that determines that the proportionality. So this could be my simple law that determines how A gets converted to B. Obviously, there could be many other things I could pick here, but this is a good one. It matches most experimental evidence. This is what's called mass action kinetics. Of course, if I have an enzyme, I might have to use, some enzyme kinetic law. There are lots of possibilities here, but we're going to try and keep things simple. What happens if it were reversible as well, that B went back to A? Well, I just add on a minus term. That's why this should have been a minus here, because this corresponds to this minus here. I just have, the rate going backwards, K different rate constant, K2 times B. So I would have some, laws like this that determine how fast reactions occur. So when you had this, this complicated thing here, each one of these steps has some kind of reaction rate law that determines how fast it's going. All right. Now, what then? So when we had the tank models, I used the conservation of mass to decide, how flows move from one tank to the other. I can do exactly the same here. So if I have a little pathway, something makes a species S, and then something else degrades a species, I can tell you that the rate of change of S is simply how much is coming in minus how much is leaving. This is just a restatement of the conservation of mass, okay? And in fact, in general, if I have lots of things coming into S and lots of things leaving S, I will just have a sum of things coming in minus the sum of things that are coming out, right? So every node, yep.
There's another typo. The out should be V2 on the top line.
Oh my goodness, yes. Yes, you're right. So yeah, for those of you who didn't spot it, that should be V2, okay? Yeah, good. So that's basically how you do it. So if you have a picture like this, you'd pick a node. Yeah, folic acid is a nasty one. Look, lots of things leaving and lots of things coming out. So the rate of change of folic acid would be equal to the sum of lots of things making folic acid minus the sum of lots of things consuming folic acid. Okay. Now I can go crazy here now, and I can have a much bigger network. So this is a bigger one. This has 1, 2, 3, 5 reactions, 2 species, S1 and S2, 2 branches. Looks like I mean, I haven't talked about the inputs or anything here, but presumably V1 is an input because it's feeding into S1, right? You'll have to decide that when you build the model, what's the input and what the output. There may be, I don't know if there are any other inputs in this system. It looks like just that. Although if these were enzyme catalyzed and had the ability to change gene expression, I might include those as inputs too. Your choice of inputs will depend completely on your model. Mainly depends on the questions you're asking, okay? What kinds of things you can change. This number of state variables here, well, it's S1 and S2 that'll go up and down. I don't have direct control over those because those are determined by the model itself. There are no, I don't see any parameters here, but they are here. And they're buried inside the reaction rates, okay? So, and if you look at the rate law, for example, sorry, these rate laws here, these are actually the parameters K1 and K2, all right? So the parameters are buried inside the reaction rates. So how would I, describe a model for this system? The 2 state variables, S1 and S2, and therefore there are 2 differential equations. I can now use conservation of mass now to write down the right-hand side. Remember, it's the sum of what's coming in minus the sum of what's leaving. I have 1 thing coming in, or I have 2 things leaving, okay? So that's V2 minus V2, V1 minus V2 minus V3. For S2, I also have 1 thing coming in, and I have 2 things leaving.
You highlighted the wrong one. It's you highlighted V4, but you meant V3 because it's
Oh, right.
About for S1, the change in S1 is V2 and V3. It's because it goes directly out of S1. There you go.
There you go. Yeah, those are the two that leave. That's right. Those are the two that leave. And for S2, these are the two that leave. Okay, so that's how you'd build up, you could build up a big model this way by taking each variable, right, each species, and then constructing all the inputs and outputs for each one. You can go even crazier. This is another one. Instead of writing a picture now, I've written a scheme. I could turn this into a picture if I wanted to, but you need to get used to these kinds of scheme diagrams. So I've written this as a scheme. This simply means that A plus X combine to form 2X. X plus Y combine to form Z. Z breaks up into Y plus B, all right? So I want to convert that into a different set of differential equations. There's one little complication here because I got X on this side and 2X on this side. What this means that there's only a net production of 1X in the reaction cycle. So when I write down dA by dx, it is actually only, there's only one thing that's leaving. Let me back up a bit. There's only one thing leaving A, and that's V1. Only one thing consumes A, so there will only be one entry for A. A doesn't occur anywhere else, okay? So only one thing leaves A, and that one thing is V1, and to indicate that it leaves, of course, I put a minus in, all right? Yeah, the complication comes with X, actually. X appears twice in V1 and once in V2. Let's do the V2 first, because that's the easiest. X disappears in V2 because it's on this side. So X disappears. So I have a minus V2. However, it's obviously being used and made by V1. It's being used by a rate minus V1, but it's being made by a rate 2 V1. So if you combine those together, you get a net rate of V1, which is why then I have only V1 here. You need to think about that. If you don't quite get that, we can discuss it later. But think about why we've only got one V1 here. The Y should be straightforward. Y is disappearing at V2, but it's being made here at V3. So I got a plus V3. Same, the Z is the same, similar. And the B here, well, B only occurs once, and it's being made at a rate V3. Okay. Just want to mention one last thing here. Let me think. I'm not sure how important this is, actually, mentioned at this point, given the time. But there's a compact way of representing all these equations in the form of a stoichiometry matrix. This basically takes all the signs you see here. There's a minus here, plus there, minus here, plus there. Takes all the signs and puts them into a compact matrix form called the stoichiometry matrix. All right. So the rows correspond to the species and the columns the reaction rates. Just to give you an example, if I have this linear chain here, 1, 2, 3, 4, 5 variables, and 1, 2, 3, 4 reaction rates, I can convert this into a stoichiometry matrix in this way. These are just the signs on the V's, V1, V2, and V3 that appear when I rewrite it as a set of differential equations. I'm not going to dwell on this because I don't know how important this is for this week, but it's there if you, stoichiometric matrices are used a lot. If you see it, this is basically what they mean. Okay. All right. We've got 10 minutes to go before we break for lunch. Is that right, Veronica?
Yep, that's right.
Yeah. Right. So the last 10 minutes I want to spend, sorry, I got a cough. I want to spend one last thing talking about wiring diagrams. This is something that was asked that the CompuCell 3D week need. So let me start by showing you some figures. So this is a typical diagram you might find if you do some searching on on Google. This happens to be a signaling pathway. And what you see here are a variety of different kinds of arrows. You see here this RAF arrow mech. I wonder what that means. And then you have ERK here with a blunted-ended arrow. I wonder what that means. And the question comes is, you know, how do you convert this kind of thing into a model? What do these arrows actually mean? And I just want to briefly comment on that. So we've got at least two kinds of lines here. We've got arrow lines and blunt end lines. Here's another one. This one is really crazy. This one, this is a stem cell model. Those of you, these are transcription factors, NANOG and SOX2, and OCT4. You see we've got a mixture of arrows again, and we have blunt ends. All right, so it tells you here that the blunt end is repression and the arrow is activation. So how do you interpret these and convert them, you know, into a model? So first of all, we have to understand what we mean by these. Blunt ends. And notice also that these blobs here, for example, GCNF, just seem to end. It seems to suggest that stuff is GCSM is being made by GATA6 and GDX2. So wouldn't that suggest that the GCNF would just keep on increasing forever? No, because in this diagram, what the authors have done is they've missed out a degradation rate. They've tried, I mean, the diagram is complicated as it is, right? So they've tried to simplify it by removing all the degradation rates from these nodes. So there are missing things from this diagram. So that's the first thing you have to be aware of. The second thing, they say now that GCNNF somehow represses OCT4. I mean, how does that work? You can't actually repress a species itself. All you can do is convert it to something else. Right? That's the only way you can repress a molecule is by removing it, and that means converting it to something else. So this actually is a shorthand notation for actually a reaction. So let me let me start here by showing you these two here. So I want to show you these two here on the left here. We have a reaction, S1 goes to S2, and we have an A here representing an activator. And you can imagine that as we increased the activator, that the S2 would go up. All right. Now, another way of writing this is in a way, the way they've written it in the previous model. We don't do it as a reaction, but we do it as an interaction or an influence diagram. We say that A influences S2, right? Yeah, it might be clearer here on the one below where I have the same reaction, S1 goes to S2, and it's repressed by a repressor R. So when you see a blunt end, you know that means repression. Another way of writing this is just to say that R represses S1 in some way, but it doesn't specify how that happens. And so if I plotted S1 against R, I get a decline in S2. This piece here is what is written here and is what is written here. Right? So whenever you see something repressing a molecule, it actually means that there's a reaction where the molecule is being converted into something else, and it's the rate of the reaction that is either being repressed or activated. So all diagrams like this can be converted into reaction form, you know, if you look at them closely enough. And here's a good example in the last 5 minutes. There's a gene regulatory network. This is a notation here that's used by biotapestry. It's a very concise notation. What I have here is a gene P, that makes messenger RNA, that makes protein. Lots of things are missing here. For example, the degradation of messenger RNA and the degradation of protein. But what I have here is an inducer I that induces the expression of mRNA, okay? Now I could simplify this by removing the mRNA, and I just have inducer activates production of protein P. Okay, I could do that, right? So let's have a look at different ways of expressing the same thing. And you'll see this a lot in the wiring diagrams. So for a gene network, so this is the gene network here. So protein P1 activates production of protein P2. I can write this either as P influences the production of B2, or I can write it as a reaction where something makes P2, which is influenced by P1. Right? If I do it by a reaction, I can't put P1 here because that would suggest that P1 is being used up. But P1 is not being used up. It's an inducer. And so the way I would write it then is that something, I'm not going to say what, but in this case, it would be, you know, I suppose, the gene itself, amino acids, ribosomes, and so on. I can assume those are constant. They contribute to making P2, but its influence are regulated by P1. And so when I write down the reaction rate, I write it down as a function of P1. So you may have to do this in the next few weeks where you see a diagram like this, or a diagram like this, and you have to convert it to a reaction form. Here's one last example, and I think that's it then, where it shows two examples. I have the top one and the bottom one. So what we've got here, the simplest one you might find in a textbook is that P influences the production of P2. Right? Now you might re-express this as a gene where P2 is influencing the production of P2 like this, and there's a degradation rate. Or you might expand this and say, well, actually the gene produces messenger RNA, which influences the production of P2. Both mRNA and P2 have degradation rates. So your model can be written in various forms, and it depends on how much detail you want to include and how much detail you want to leave out. But for our purposes, we always have to convert something like this, P1 influences P2, or P1 influences the production of P2 with degradation, into a set of chemical reactions. All right. And in this case here, this expands. Which one does this expand? Yeah, so this one here, let's look at the bottom one. This one expands the second model into a set of 4 reactions. First reaction makes mRNA, so that's V1 basically, and it's influenced by P2. The second reaction degrades mRNA, which is D2. This is a function of mRNA. Okay. The second reaction, this one here, mRNA is influenced by B2, and P2 degrades D1, is in 2 reactions. V2 is influenced by mRNA to produce P2, and then the degradation rate, D1, is just a function of P2. So this single model here, P2 influences P1, has been turned into 4 reactions with 4 rate laws. And so in the work we're doing, most of the platforms we use, whether it's Tellurium, Copasi, vCell, et cetera, they all express things in terms of reactions. And you have to learn how to take a diagram like this and then convert it into a set of reactions. So you might see some of these over the next 3 days. And if you have any problems or puzzles as to why it's expressed in a certain way, don't hesitate to ask. So this has been pretty quick, and I may have lost a number of you in this, but look at these slides. And if you have any problems, just send questions to us on Slack, preferably, because the channel will disappear today after today, but the Slack will persist. And so if you have any questions about this, don't be scared to ask the questions, no matter how silly they may seem. Just ask the question, and we'll try to answer it for you. All right, that comes to the end of this morning's session. Thank you for your patience. I hope you've managed to get something from this. We're going to go for a lunch break now. If there are any immediate questions you want, we could spend 5 minutes answering them now. So any questions, fire away on Slack or chat.
Someone was asking about the degradation of P1 in this model. We're assuming P1 is a constant.
Yeah,
but you didn't have to make that assumption. That was just an
That's
assumption.
right. That's right. Yeah. Yeah. When you build a model, you'll make lots and lots of assumptions. And you'll have to gauge those assumptions based on the biology you know. Actually, notational wise, it would probably been better if I'd instead of using D1, I use something like V3, because these are actually the rates. So I should have used V3 here and V4 here probably, rather than D1 and D2.
Veronica, is there? Can we get a link to the Slack channel? Someone messaged me. Just
Yep,
yeah, that'd be great.
Okay, so I think that's right. Yes. So we tend to use arrows to mean movement of mass, circle end to use activation, and blunt end to use repression. Yeah.
But like you did show a diagram where an arrow didn't mean movement of mass, it meant activation instead, right?
That's right. I've probably been naughty here somewhere. Where was I naughty?
It
Somewhere
was
here.
this one, yeah.
Well, yeah, that's not mine though. But yeah, this is
yeah.
There's no consistency in the literature, which is why I was asking, what does this arrow mean between RAF and MEC? Does it mean RAF influences the production of REF, or does it mean RAF gets turned into MEC? And this is a bit of a problem. I mean, the electrical engineers have it easy, right? All their diagrams are very consistent. They follow the rules, but we don't have any rules really about how to draw diagrams, and all our diagrams are all over the place. So we try to be more consistent, and round arrows for activation, arrows for mass movement, and blunt ends for repression. So. Yeah, books. What we have, I don't know if you can, let me stop sharing my screen. I mean, I'm going to sell myself here. Okay, so for textbooks, we have this book, which is has a lot of the same material in it. You can get it, I think, for a PDF for about $7, but I could do a special deal for people if they want to on this course, just for a couple of dollars to get the PDF. Just this one, and then there's also an enzyme kinetics book for the same thing. You can get the PDF as well. We can sell it. I can get it to you for a couple of dollars if you want. The printed copies are, of course, available, but they're more expensive, of course. But they're still cheap compared to most textbooks. Okay, you can get them from
website?
Amazon.
Oh, just on Amazon for the
yeah, for the PDFs, you need to go to Tindy. Let me get the reference for you. There's a website that lets you sell electronic goods. I mean, you know, PDFs and things like that. Let me see here. You're probably not seeing anything at the moment. Let me just share my screen and show you what I'm seeing. Where are we? Yeah, there's a thing called Tindy. I suppose I've got to log in, I suppose. Come on. Okay, here we go. This is it. Yeah, there's a thing here. Actually, those are the purchases. Sorry, I don't do that with my products. Here we go. So, except those are the wrong ones. Where it must be in a. Hold on. Let me. That's the wrong one. Let's go to books, analog machine. I think it's here. So you can either go to Amazon and just look up systems biology or enzyme kinetics, or you can go to this site, booksanalogmachine.org. I think it redirects then to Tindy. Hold on for a second. Here we go. So yeah, you can either purchase them at Amazon. Here, there's a link here, or you can purchase them at that place, which is at Tindy. It should be. There we go. Where did it go to? Oh, it's not Tindy, Gumroad. Yes. So there's another site called Gumroad. Yeah, I go to too many places. Let me see, Gumroad. Oops. Go away. I don't know why it's doing this to me. Don't want to do it. Sorry. Is it? Maybe it's Gumroad, is it? I've forgotten where I even sell my own books. No, here we go. So if I type systems biology, lies. They're definitely there. Actually, if we go back to this site instead, sorry, I'm jumping around here. Where did it go? Let's go back to here. Let's see, textbooks. Textbooks. Introduction to Systems Biology. So that's the textbook, and it's probably there. That's it. Yeah. So that's the site. That's the site here. So if you go to analogmachine.org, okay. So I'll put this in the.
Yeah, that's already in the chat.
Right? And then you can just go to textbook and then just pick one of the textbooks. And if you pick one textbook, you either get it from Amazon, all right, or you can go to, or you can click on the textbook itself. No, that just gives you. How did I just get to it? Oh, did I go? Oh, here, yeah. Then go to the textbook entry here, and then this one will purchase it directly for those in the US. Or if you go here, you can order the PDF. Okay. I'll put more details out, and it's not wasn't that clear. Okay. Anything else? I can set up a special link to purchase the PDF.
So it seems like that was an older version. That was 1.3. Don't you have an updated one?
That's a good question. I'm currently, the newest version is 1.2. I'll check. I'll make sure they're up to date. Yeah. Yeah. That's a good question. Yeah, I keep updating them as well. So they've gone through quite a few revisions. Okay, I think that's it then. Unless there's other questions, I think we should all take a break, have lunch, etc. And then I think, Veronica, you're going to be starting at 1?
Yep.
Okay, same place, but in roughly 1 hour's time.